All right. Good morning, everyone. So we are going to be together for 3 hours and a half, and we are going to talk about databases, basically, and all the different kinds of data that are out there. So my name is Andrea Brunello. First of all, I am an assistant professor tenure track at the University of Udine. I am a member of a laboratory, which is called Data Science and Automatic Verification, and I invite you to visit both the web pages. The first one is my personal web page, where you can find information about my research, the courses that I teach, and so on and so forth. Whereas the second one is the page of the lab. So there you can find also things about collaborations that are going on with companies. Currently, we are working on a new site. This is the old one, let's say, but still, you can find all the information there. Because we have several opportunities, you know, thesis, PhD thesis, master thesis, also internships, and so on and so forth. Just have a look. Just to give you an idea about the things that we do there, we work with artificial intelligence, of course, applied to several domains. So we work in the healthcare domain, and we work with the university, Udine University Hospital, basically. We work with localization, so how to localize people or things within buildings using wireless signals, such as Wi-Fi. We work in the digital humanities field because actually I am a computer scientist, but I belong to a humanities department. So we apply artificial intelligence also to archaeology, let's say, and those kind of stuff. And finally, we are also working on the topic of symbolic and symbolic AI integration, so level of symbolic integration and those kind of stuff. Just to give you a very brief look at what we do there. So, as for what we are going to do today, we said we have 3 hours together, which is quite a long time, but we have a lot of stuff to cover. First of all, we are going to explain what databases are and why they are important, basically for everyone, we are going to see. We're going to see that there are several kinds of data out there, and for that reason, there also exist several kinds of databases to handle them, which can be quite different with respect one to the other. Basically, we are going to distinguish between SQL databases on one hand, also called relational databases, and NoSQL databases on the other hand. Then we are going to talk about data warehousing, which is a technique that basically allows you to put everything together, all the data that you may have scattered in several systems within your company. You can put them together into a single container to then perform analysis. And finally, we are going just to touch the different kinds of analysis that you can perform on your data to extract some value. Of course, these topics ideally should have an entire university course dedicated to them. For instance, just for what concerns this part here about relational databases, it is typically covered along 2 different semesters in a university. So we are not going to see these kind of topics in much detail, but still you are going to get an overall understanding of them, so that you can navigate and explore them further as you wish. Okay. So let us begin in the most natural manner, and let us define what a database is. So we're going to start from the definition of database management system, where a DBMS basically is a system that contains 2 things: a collection of data which is interrelated, this data. So data refer one to the other. And on the other hand, we have a set of programs that you can use to access this data, to read them, to manage them. So data and programs to manage this data. So just to set an example, if we focus, let us say, on the insurance domain, data may be about customers, maybe about insurance policies, about claims, goods that have been insured, and so on and so forth. Whereas the programs that can be used to manage this data may be programs that allow you to add a new customer to this bunch of data, to open a new claim, to perform a risk assessment, and so on and so forth. We could make a lot of examples of databases in several domains because databases are behind the operation of basically all the stuff that you use with your smartphone. There is a database behind WhatsApp, a database behind Amazon, Facebook, YouTube, behind the bank application that you use. Everything is basically backed up by a database. So this means that databases are really pervasive. So this topic is something that should be at least understood by every computer scientist or every person that interests into this kind of topics. Okay, a thing that I haven't said till now is that you can interrupt me every time if you have questions, doubts, or some observations. Also because if you have a question, maybe also other people are thinking about it. So don't hesitate to ask. Also, if you would like some more information about something, everything. So we said that databases are quite important. They are pervasive. And so actually, people have started to feel the need about building such kind of databases right from the beginning of computer science. So we have the first examples of databases that go back, I would say, to the 1950, around that. But at that time, things were very simple. Basically, just people used files stored on the disk to manage information. And then they used to write down programs to access these files and to modify them. So to make an example, think about this situation here in which we want to store information about cars, about people, and ownership, and an ownership relationship here. So which person owns which car. We may use just 3 text files to do that. You can see here text files, the file that stores information about cars. So we have a first row that says, okay, this file is going to talk about plates, years, manufacturers, and models. And then you have 4 different rows. Each row, of course, pertains to a different car. We have a first car, which is displayed here, AX 25 to KF, manufactured in 2015 and is a Ford Mustang. And then so on and so forth. We have this other car here that is a Dodge Charger, this car, a Chevrolet Corvette, so on and so forth. So basically, a row for each car. Things are similar there, where you are talking about customers or people in general. You have people which is described by 4 different features. So the name, the surname, birth date, and gender. And for instance, you have here John Doe, who is born in 1974, and he's a male. And then also for the other people there, which are 6 people overall. And now have a look at this table here, which is called belongs to. In this file, we have 3 different attributes or features, as you would call them, which are plate, customer name, and customer surname. And you can see that using this file here, we can somehow link these two together, because here we are saying that the car with this plate, which is this one, is owned by John Doe, who is this one. Then, in the very same manner, this car here, BK, which is this, is owned by Mary Jane, with this, and so on and so forth. So somehow we are linking information together. So actually, just by using files stored as they are on the disk, we can start to memorize information, and then you can very well think that you might design a program in Java, in Python, in whatever, that can access these files and write a new row within these files, or delete a row, modify a row, and so on and so forth. So we have our first solution, but of course, databases are not made like that today, because this kind of solution brings a lot of problems, especially when the amount of data that you have to handle grows over time. First of all, you find yourself having data redundancy and heterogeneity problems. Okay, we've seen that here we had just 3 different files, but if the domain that you want to model, that you want to manage is, let's say, complex enough, then the number of files will get bigger and bigger. You may find yourself having tens and tens of files. And at a certain point, it might be that the same information which is contained in a file, for instance, information about the customer, is stored also within another file. Maybe you do not realize them, but somehow you store the phone number, let's say, of this person as a customer in a file, and as another kind of role that the person has in another file. So you have 2 different phone numbers associated to the customer, to the person. And if everything goes well, the 2 phone numbers are the same and you're happy. But it can happen that maybe at a certain point you want to update the phone number of this person. You remember that you have one of the 2 files here and you modify the phone number, but maybe you forget that you have the other file, and so the other file still has the old phone number, and then you cannot understand anymore which is the correct one. So you can end up with data inconsistencies also, if you have information which is stored in multiple places, in multiple files. Also, given the fact that you have a lot of files here, maybe these files have been created over time by different people, maybe different programmers which have been hired by your company over time. Maybe different files use different formats, different conventions to store the data, because they have been built by different people. And this is another problem, of course. Another issue that you have with the files is that it is difficult to access the data, because to access information, you have to write down programs to do that. Imagine that you have all of these files that describe the items that have been sold by your company to customers. Then you want to know how many pairs of shoes you have been selling the last year. Well, if you just have that file structure, you have to write down a Python program that opens these files with the numbers, then calculates the sum and so on. And this is basically, it's a low interactivity manner to interact with stuff, because you have to write down everything to perform any kind of task. Then another thing pertains to constraint management. You know, different domains typically come with different constraints. So for instance, in the insurance domain, the value of a car cannot be lower than 0, hopefully. In the university domain, for example, in Italy, marks are between 0 and 30. in an exam, so they have to be within that range. Of course, to enforce those constraints within the files that we have seen before, you have to write down the programs that modify those files correctly. And this is a first problem. The second problem is that if you just work with files and programs, you do not have a single place where all the constraints are listed. So there is not a single place that summarizes all the constraints that are in place in your domain. They are just scattered around the programs that you write. Okay, these are, let's say, a first bunch of problems. Then there are some other problems which are a little bit more subtle. And the first is the atomicity of updates. Think about this situation. You are in a bank domain, so you have your files there that store information about bank accounts with owners of the bank accounts, the amount of money that this bank account has, and you want at a certain point to transfer money from one account to the other. So how do you do that mathematically? You basically read the amount of money that the bank account has. You decrease this amount of money by the amount that you want to transfer. Then you read the amount of the other bank account and you sum that amount of money. So more or less, I would say there are 4 different operations to perform this transfer. So you read, you subtract, you read, and then you sum. These 4 operations, basically. You write down a program to do that, but then you run the program to do the transfer. What happens if maybe the electricity goes away in the middle? What happens if the system breaks down after you have decreased the first account, but you still have to increase the amount of money in the second one? What happens to that amount of money? If you do not take care of such conditions when writing down the program, and it is not easy to do that, if you do not take care of that, then basically this money gets lost. You have subtracted some money, but then you lost them when the electricity went down. And of course, this is not a good situation. That is to say, is that if you do not consider this let's say, possibilities that can happen, this kind of failures of the system may leave your data in an inconsistent state. This is named in the database domain as the atomicity of updates. When you say atomicity, it means that an operation which is composed of several sub-operations, as this bank transfer, should happen totally as a whole or not at all. You cannot have a situation in which something happens and something doesn't happen. So all the sub-operations are performed or none of them. This is referred to as atomicity. And you always want to have that.
Actually,
yeah.
So if light turns off and then I extracted some money and then it turns off, can I just try to put it back when it turns off and then finish the job when it's on?
That is okay, but you have to implement it within your program. Yeah, okay. You are saying basically, okay, I have decreased the first bank account of 5,000 euros, for instance. Then everything breaks down. When the system goes up again, can I simply sum back the 5,000?
Can I just finish putting this money I didn't wait? Then can I just finish the other bank account to finish my operation?
Yeah, you can do that. Of course, this is a solution, but then it means that you have to have a kind of strategy to that. Maybe you write down a log on the disk that keeps track of the things that you are going to do. And then when the electricity comes back, you read the log again and you say, okay, I still have to do this kind of stuff. But you have to program that by hand. If you just write down a program that does those 4 operations that I mentioned, it doesn't work because you do not have memory of what you did. But that can be a solution, of course. Was it clear?
Yeah.
Okay. That was the first subtle problem. There is another subtle problem, which is even more difficult, I would say, to deal with if you do that by hand, which is concurrency. Concurrency means that multiple users want to use the database at the same time. Think about another example now. There is a database used by an airline company. And within this database, for each flight, we keep track of the number of seats which are available. Let us say that there is a flight which has just a single seat which is available. And there are 2 different travel agencies where 2 different people come. The first person says, okay, I want to book that seat, which is free. And also this other person says, I want to book a seat on that flight. The travel agency checks for the availability of seat. Both travel agencies see that there is a single seat available. And so they both say, okay, you can have the seat. Then you proceed. And you basically end up with a flight which has -1 seat available at that point. Right? Somebody has somehow to not leave if he goes to the airport, and this is something which is not trivial to be solved. So maybe you can use some timestamps. You can say, okay, you arrived a little bit earlier to the agency, so the seat will go to you, but still is something that you have to manage by hand. Finally, we have also security problems if we use files on the disk, which are rather trivial actually, because if you just have all these files, how can you provide access to a person to just some of these files and not the others? So how can you say to a person, you can read these files, but you cannot read these others? It is not very convenient. Of course, there are methodologies to perform some encryption, which depends on the person that should read them, but it is not so convenient to do that. So there are many problems and many subtleties that we have to handle. But the good news is that other people noticed that over time. And actually, relational databases, which we are going to see now, provide automatic solutions to all these problems. So all of this stuff that I've been mentioning, problems regarding concurrency, regarding atomicity, these kind of problems cannot happen if you use a database. And you do not even typically, as a user, have to care about these problems because the database automatically, the software automatically deals with them. So a database can give you a guide hand, let's say. Okay, now that we have understood what a database more or less is, we have seen a trivial solution to implement a database that has a lot of problems. We should now understand which are the kinds of data that one may be interested in storing within a database. And we should begin with saying that typically the data considered by databases used to be very simple. It used to be data similar to the one that I've been showing you before regarding cars, regarding people that own cars. So basically, tabular data, structured data, as it is called. This has been true starting from the 1950s up to the 2000s. But then, following the rise of the internet, the social media, and all the multimedia applications, we started to have the necessity to store different kinds of information. So we then started to talk about also semi-structured data and unstructured data that we are now going to see. So let us focus on these three kinds of data now. So structured data, as we already mentioned, is the most simple kind of data that you can store within a database. And structured data can be actually seen like an Excel table. So you have different rows. Each row pertains to a different instance. So here a different person. You have that each person here is described by a fixed number of columns. Every person has the same number of values here. You cannot have that a person has a different number of values, of course, because you cannot have rows with different lengths within the table. You can see that storing data in this way is very convenient if you want to perform lookups, for instance, to perform a search on this file. So this kind of data is very easy to handle somehow. However, as you may very well think, a table can convey just a limited amount of information. You cannot store everything within a table. If you have a picture, if you have a song, how can you store it within a table? It's impossible. But still, I would say that the 90% of the data is like this within a database. Then, if we move from this very simple kind of data to something which is just a little bit more complex, we find semi-structured data. This kind of data do not have a tabular structure, do not have a fixed structure, but still they have some structuring within them. And specifically, there is the presence of these so-called tags, which are just markers, if you want, that can guide you in reading this data. So for instance, here we have an XML file. And this file is storing information about telephone surveys. You can see that we have these two tags here from campaign. This tag is an opening tag, this one is a closing tag. You can see that there is a nested structure. Here we have two different surveys, survey 1, which opens here and closes here, and survey 2, that opens and closes. For each survey, we have the name of the person who has answered the survey, but then you can see that the remaining part of the surveys differ. So here we have these 3 questions with this ID, and here we have 4 questions, and these 2 have a different ID with respect to this, and also we have a different field here, which is called note, that is not present here. So already in this way, you can store something which is a little bit more heterogeneous with respect to a table. Reading a file like this one is still simple. You can think about writing a program that just navigates this kind of tree structure, reading this text, and then the content. Okay. But then this is just an intermediate case, and the most complex case is that of unstructured data. Unstructured data is not organized in any quantified manner, so there is no structure here, of course. Examples of unstructured data are free text, so free text annotations, audio material, visual materials, such as pictures, songs, and so on and so forth. Of course, this kind of data are the ones that can, in principle, convey most information. They are very rich data, but they are conversely very difficult to store, to index, and to analyze. So for instance, just think about having a large set of pictures. It is difficult to perform a lookup within these pictures. How can you extract, for instance, all of the features of an accident that somehow is similar to this one, with a car hitting another one on the left side? You have to have, of course, but well, now you can use maybe deep learning to have a look at the pictures, then you try to extract the semantic content, but it is much more difficult than, of course, making a search within a table. Okay, so you have now seen that there are these three different kinds of data: structured, semi-structured, and unstructured. What we are going to do next is to see how you can store them within a database. And we are going to start from the most simple case, that of structured information, which is then also the most common one, I would say, still. And to store structured data, you typically use relational databases. So relational databases represent information in the similarly to an Excel file. So they represent information by means of rows and tables. And this kind of databases have been proposed in the 1970s, so they are quite old now. But still, they are the most common one within companies and within institutions. And this is because these kind of databases here have a clear mathematical formulation by which we can express several nice properties about the data, consistency properties, for instance. Also, these kind of databases are simple to interact with because, of course, they take care of all of the problems that we mentioned before. But also because relational databases come with SQL, which is an acronym that stands for Structured Query Language. And SQL is, as we are going to see, a very user-friendly language that allows you to define a database, to insert data in a database, to retrieve information, and so on and so forth. Yeah, that one is Tadcom, the one that designed relational databases. Okay, so let us say that we are in this situation. We have our relational database that we said stores information using tables. We have two different tables, specifically. We have a table which is called employee, and we have another table which is called department. The idea is that employees, of course, belong to departments. They work for different departments. You can see that for each employee, we store a lot of information. So the social security number, name, surname, gender, birth date, salary, and the department where the person works. Other than that, you can see that for every column, other than the name, we have the data type. So for instance, we know that first name is of data type text, so you can write strings within there. Birth date is of type date, so you can just write proper dates. Salary is numeric, so you can just enter numbers, and so on and so forth. This is just something which is a little bit better than files on the disk. At least here you can control the kind of data that you insert within a table. If you just write files on the disk, you can write whatever you want instead. So this is just a first kind of constraint that applies to the table. You cannot write everything that you want there. You have to satisfy these domains, these data types. The second important thing that we can notice here is this PK here. This PK means that this column is the primary key of the table. This means that you cannot have two different rows within this table with the same value for this column. So if here you have this code, you cannot have two times in this table this code. And this prevents data redundancy. Because if you enforce this constraint, the system won't allow you to insert two times this employee within this table. The other very important thing that we can notice pertains to combining the two tables here. So we said that each person here belongs to a department, for instance, to the department sales here. We have a table department with its columns. Notice that here we have a column code, which is also the primary key for this table department. And notice how the word, the text here appear also here. So you can see sale, but sale is also here. See service. So you can see that somehow these two columns build like a bridge between the two tables. And a nice thing that you would like to have to maintain data consistency is, of course, that if you hear in table employee mention a department, so if you say sales, of course, you want such a department to be one of the departments which are present here to maintain a proper link between the two tables. So, for instance, here, I cannot write research because here research is not present, there is res, but not research. Okay, so you can already see how the systems provides you tools to maintain data consistency, both within the single table and also among multiple tables. This is called a foreign key constraint. The constraint that you can specify between these two fields to say that every value here must also be present here. And these are not the only kind of constraints that you can specify in these databases. I would say that they are the most important. Here I just listed some other ones, but be aware that there are several others, not just these ones, that you can employ to enforce the correctness of your data, to make your data, to keep your data clean, to keep your data consistent. Other than all these constraints that you can employ, keep always in mind that relational databases automatically deal with all those bad stuff regarding atomicity and concurrency that we mentioned before. So the two examples regarding the bank transfer and regarding the airline ticket booking, those situations cannot happen here if you use this kind of systems, by definition. There are several vendors out there of relational databases, given by the fact that they are so popular. Of course, there are some major companies. For instance, we have Microsoft with SQL Server. We have Oracle with MySQL, and of course, Oracle. But there are also some open source solutions. And the most popular one, I would say, is PostgreSQL. And while it is true that Postgres is an open source solution, it is free, it is still one of the most used databases. So Postgres is actually very sophisticated and it can compare quite well with these other solutions, which instead are commercial ones. And the very nice thing about Postgres is that there is not even a company that develops this kind of system. It is just a set of users scattered around the world that coordinate between them using a forum or other media, and then keep on with the development. Okay, so relational databases. We have been talking about how they keep your data clean and how they help you with solving those kind of anomalies that can happen interacting with them. We still have to mention SQL, which is the ultimate reason, I would say, why relational databases are so popular. SQL can be used to do basically everything you do with a relational database. If you have a relational database, you just use SQL to interact with it. So this kind of language has several functionalities within it. You have the data definition language functionalities that allow you to define tables, to define constraints over these tables. You have the data manipulation language part, by which you can insert, update, or remove rows within a table. And then several other stuff that, well, it's not necessary to mention now. Just a couple of words about the story of SQL. SQL was born in the 1970s together with relational databases, and it was born within IBM historically. Then SQL over time became an ISO standard in 1986. And then this standard has evolved over time, and the last version is now SQL 2019. So this language has been standardized. However, it is also true that different database vendors implement slightly different versions of SQL. So the language SQL that you find in Microsoft SQL Server is a little bit different than the one that you find in Postgres. Not that much different. If you can write this SQL in Microsoft SQL Server, you can also know how to write it in Postgres. But still, if you write down a program for one system, most likely it won't run on the other one straight out of the box. You have to modify something. Still, the core functionalities of the language are largely equivalent between systems, and we are going now to see just the very basic of that. So let us consider how you can extract information from a database using SQL. To do that, you basically write down a query. And the most simple query that you can write in SQL is composed of 3 different blocks, which have 3 clauses: select, from, and where. From allows you to specify a set of data sources you are interested to. For instance, a set of tables from which you want to get the data. Select allows you to specify which columns you would like to get from these tables, other than other kinds of mathematical expressions you can also specify there. Then you have the where condition, which allows you to filter rows. So you can say, get me this row from the table if it satisfies a certain condition. Other than these clauses, there's other ones which are order by, having, and group by, which we are not going to touch today. So let us just see a couple of examples. And we are going to see that SQL is very nice because when you write a query in SQL, it closely resembles the way in which you speak. So for instance, if you want to extract the name, the surname, and the monthly salary of all the employees of gender female, and with a total salary greater than 60,000 from your table. Remember that your table is made like this. You can say, well, from table employee, select the first name, the last name, and the salary divided by 12, because you want the monthly salary, where the gender equals to female and the salary is greater than 60,000. What happens here is that the database goes to the table, looks to the table employee, looks for the rows that satisfy this condition here, and you have these two rows, because these two rows have gender female and the salary greater than 60,000. And then just from these two rows, it will return the first name, last name, and here salary divided by 12, which is the final result that you can see on the right. Just to show you that you can do something else in this select clause rather than specifying just column names. Let us say that you want to extract the average salary of employees working in the sales department. Again, from table employee, where department equals to sales, and we have got these two rows, give me the average salary. And this calculates the average between these two values, basically, which is the result that you get on the right. And then we have our final example, which is a little bit more complex because it involves using two different tables. Let us say that we want to extract the name and the surname of employees working at a department with a budget greater than 720,000 euros. You can immediately see that we cannot answer this query using just a single table, because in the table employee, here we have the information on the department in which the person works, but here we do not know anything about the budget of this department. The information about the budget of department sales is on the other table, is on the department table. So somehow we have to combine these two tables together to answer the query. And I would say, first, let us read the query, and then let us try to decompose it to see what is going on here. But first, let us read it as a whole. So, select employee.first name, employee.last name. So these are the two things we are interested into. From employee, join table department on employee.department equals department.code, where department.budget greater than 720,000. This is the query that answers what was asked before, and now we are going to see what is going on here. So, the first step is that of performing this thing here, this join operation. The join operation basically puts together two different tables. So combines the rows of one table with the rows of the other. And when you do that, of course, you want to combine them in a manner which makes sense. So you specify a condition here to perform the combination between the rows. Here we are asking that the field which is called department in the table employee equals to the field which is called code in the table department. So what is going on here is that the system first combines every row of employee with every other row of department. So you can see that here, for instance, we have John Smith which is repeated 5 times, and every time is combined here with a different row of the table department. And the same happens also with Frank Doyle here, which is repeated 5 times, because it is combined with every row of the department. It is a Cartesian product, if this term helps you, basically. Then, when we combine every row of a table with each row of the other table, we just keep the combinations that satisfy the joint condition. Our joint condition was that these two fields here have to be the same. So now we are just keeping the rows. You can see that this row here makes sense, because here we have information about John Smith, who works for sales, and here we have information about the sales department. Whereas this row here didn't make sense, right? Because we had John Smith, who works for sales, but here we had information about another department. Okay? So just these rows that make sense are kept. Then the where condition is evaluated, and we wanted to keep the information just about the people who worked in a department with a budget greater than that number, 700,000. And we just have 3 rows that satisfy it. And for those 3 rows, we want to return the first and the last name. So here is the result, and these are the people who work for a department with a budget greater than 700,000 euros. At first, this might seem complicated, but if you take a second look, maybe also a third look, it is much easier than writing down a JavaScript, a Python script that reads the table, extracts everything, and tries to figure out what to do. This is much simpler. Yep. Where? Okay. Yeah.
So we can see that there is also that white also working landing. Yeah. Marketing, and it was greater than 7. It's supposed to be greater than 700.
Let's see. It was 720. Okay, that's why it's wrong. Okay. The questions? Okay. Also feedbacks if I'm going too fast, too slow, or yes, I'm going too fast. Okay. Okay. So let us just do a recap, because there are a lot of stuff that we're going to see today. So what have we seen up to now? We have seen that there are 3 different kinds of data. We have structured data, semi-structured data, and unstructured data. Structured data are the easiest to handle because they are like tables, but they provide just limited amounts of information. Unstructured data are the opposite. If you want to deal with the structured data, then you'd better use relational databases, because they help you quite a lot in constraint handling. So they prevent you from putting bad data within them. They also solve a lot of bad stuff that can happen when you update information. And also they have SQL, so that language that we have just taken a very brief look at, that makes the interaction very easy. I would say that we can make maybe 15 minutes break before proceeding, now that we have this recap. So we can meet again at 10 past 10. Okay. So we have been talking about relational databases, which are good to store structured data. Unfortunately, or fortunately, not all of the data that we have out there is structured, but we have also semi-structured and unstructured information. And so we have other kinds of databases that have been developed over time to deal with those kind of data. And particularly here, we are going to talk about NoSQL solutions. Actually, NoSQL systems are a wide spectrum of different solutions, encompass a wide spectrum of solutions, and they do not refer to a specific technology. There is not even a definition of NoSQL system, but rather you can use this one. So a possible definition of NoSQL is next generation databases, mostly addressing some of the points, being non-relational, distributed, open source, and horizontally scalable. So basically, a NoSQL system is not a relational system. That is the definition. Everything which is not relational is NoSQL. So, although SQL, NoSQL technologies are going to be very heterogeneous, as we're going to see, they still share the fact of being distributed and horizontally scalable. These are two keywords that we are going to see just in a couple of slides what they mean. It is not surprising that NoSQL proposals have been developed starting from 2009. And this has been done specifically to address all the new kinds of data that were being produced with the rise of the internet. Okay. Specifically, what happened with the advent of the social media, social network, and so on and so forth, is that data over the years got bigger in volume, increased in their heterogeneity, and also started to be generated faster and faster. And classical relational database systems were simply not designed to cope with this kind of data, which is not a fault, because relational databases were born in the 1970s and the internet didn't exist at that time. Instead, NoSQL solutions are specifically designed to deal with data which can have a very high volume, much variety, so heterogeneous stuff, and data generated at a very high speed. These three are the characteristics of the so-called big data. And to cope with these characteristics of big data, NoSQL solutions are highly flexible in general and scalable. We said before that one of the characteristics of NoSQL solutions is that of horizontal scaling. Typically, a relational database is hosted on a single machine, on a single server. And that kind of database scales vertically. This means that if somehow you need more processing power, more storage space, what you do in a relational database, you simply increase the capacity of the server where the system resides. So you add new processors, you add new disks, and so on and so forth. Of course, if you scale vertically, there is a limit that you touch at a certain point because there is a fixed number of CPUs that can stay on a server, just to say one. And also, this kind of scaling is not flexible because if your management needs require for a certain period a large number of processors to deal with the computational requirements, you add them to your machine. But then once this period has passed, you do not need them anymore, but still you have bought them, you have installed them, and then they just stay there unused. So it is not very flexible. Horizontal scaling is the opposite way to proceed. We have that the database does not reside in a single machine, but resides into multiple nodes, into multiple machines. So if at a certain point you need more processing power, more storage space, you simply add machines to your network of machines. Once you do not need anymore, you simply detach these machines from the network. And you can do that very easily if you, for instance, use the cloud, a cloud infrastructure. You buy more virtual machines, you add them, then when you do not need them, you simply discard them. Of course, if you scale horizontally, meaning that your data is scattered into several machines, this brings a lot of problems that relational databases didn't have to deal with. Because if you have data scattered into multiple machines, just to say one thing, how can you ensure the consistency between the different machines? Or what happens if one of these machines breaks down? These are a whole new set of problems that NoSQL systems have to deal with that relational databases do not have to. Okay, this is just a recap on the big data. I would say that we have already said everything here. So the only thing is that big data is actually a term which is not very new. It is from 2001. It was a Gartner analyst who coined it. Okay, just to give you an intuition about what big data are. So let us just focus on the volume of the data and on the variety of the data here. So data which are typically handled by relational databases stay here. So our data which are not very big, they are very straightforward to be stored because they are just tabular data. This can be enterprise resource planning data, supply chain management data, and those kind of stuff. But then if you move towards this direction, you find data which are bigger and bigger and also more and more complex. For instance, you may find customer relationship management data. And then, of course, the use case, which is most representative of big data, will always be that of social media, where you have a lot of data which is generated continuously and it is highly heterogeneous. Okay, this is just the last example about big data. Just to give you an intuition about the problems that we find ourselves dealing with now. So the amount of data that is generated sometimes. This is the square kilometer array radio telescope. And this kind of radio telescope produces every second of operation 160 terabytes of data. That somehow every second these data have to be handled. They are so big that this kind of data cannot be stored as they are, for instance, but they have to be analyzed as they come and then compressed, reduced in their size before being stored. So just to give you another intuition about big data. Relational databases simply cannot handle this amount of information. In the 1970s, it was impossible to have this kind of volume of data. So we have been talking about NoSQL solutions. We have said that they handle all these new data requirements. They also somehow deal with data which are scattered into multiple systems. And so why people do not simply use NoSQL databases at this point, but still use relational databases? And the reason is that NoSQL solutions have also several drawbacks. And the main drawbacks are that in order to accommodate for all these heterogeneous kinds of data, for all this data which may be very big in their volume, NoSQL solutions have very simple data models, meaning that they can enforce just a limited amount of constraints on this data, and they are not very capable in ensuring atomicity and concurrency aspects as relational databases are. Here, much more is required from the programmer to enforce them. These kind of systems help you way less than relational databases to enforce those kind of requirements. Simply because they do not scale well with the amount of data. Also, NoSQL solutions, which I think shouldn't come as a surprise, do not have SQL. SQL language, so that kind of language which is very simple, very user-friendly to interact with the system, here simply is not present. Here, you have to write down typically scripts by yourself. You do not have the join operation that combines information that stays into multiple sources, and so on and so forth. So these are the reasons why people still rely a lot on relational databases. Because if you can use them, you'd better use them because life is easier with relational databases than here. Okay, we said that NoSQL solutions are very heterogeneous within them, but still we can group them into 4 different families. We can find key value stores. We can find document-oriented databases, column family stores, and graph databases. These are basically the 4 main kinds of NoSQL systems. Key value stores are the most simple kinds of NoSQL solutions, and they are based on a very simple concept, which is that of associative array. An associative array is just a list of pairs where each pair is made in this manner. So you have a key and you have a value. Imagine a long list of keys and values. And the thing is, if you know the key, then you can retrieve the value in a very fast manner. So how can you store information using those kind of arrays? Think about the example of before about employees. So if you want to store the same content as that table, you could use several different arrays. In one array, you could store the phone number of each employee, where each employee is represented by its social security number. In another array, the department name where the employee works. In another one, maybe the budget of the department, and so on and so forth. And everything is there. So this is a key value store. You just have this associative array of multiple associative arrays that you can use to store your data. But the fundamental point is that assessing a value knowing the key is instantaneous, even if the volume of data is very big. The operations that you can perform on associative arrays are very simple. You can just add a new tuple, a new pair, remove a pair, modify the value associated to a key, look for the presence of a key, and this is it. So key value stores are extremely simple when it comes to their data model. You cannot perform some operations that instead are supported in relational databases. So in key value stores, for instance, you cannot perform complex filtering operations as you would do with the where condition in SQL. You cannot perform joins between these arrays. There are no foreign key constraints that keep the consistency between the information stored in different arrays. This is something that you have to do by hand. But still, these kind of key value stores are instead extremely sophisticated regarding how they implement horizontal scalability, regarding how they scatter these arrays into several machines, and how they cope with all the issues of this scattering. So where you should use key value stores? Typically where you have to store simple information, but this information are produced in a very fast manner, and they can become quite big. But still, you want to access that information fast. A very simple use case is the storage of fast sensor data. So remember the SCARA telescope of before. Maybe a key value store could be used to store this stream of information coming from the array. And here is just a list of the available systems. So you find typically, I would say Redis is the most common between these three solutions that I mentioned. The second kind of NoSQL system is the document-oriented database, which shares a lot of commonalities with the key value store. But here the information is a little bit more structured because here we talk about the so-called document. So the information is stored in this manner. We have a key, but then the value, you can see, can be more complex. It's not just a single value, but you have this kind of structure in within. So you remember the example that we made for semi-structured data, the XML file for the phone service, something like that. You basically associate a key to that structure that we saw before. So here, this kind of document-oriented databases represent a step up with respect to key value stores due to this more complex nature. But everything basically ends here. So still, if you want to join the information which is obtained into multiple documents, still you have to do that by hand. There is no join operation here because there is no SQL. The operations supported by document-oriented databases are very similar to the one that we've seen before. So you can create a new document, you can retrieve a document based on the key, update the content, so on and so forth. Just a curiosity, I would say. So we said that you cannot perform the join operations between different documents. So let us think about a common situation. So in which maybe you want to store information about books and about authors in a relational database, typically you have a table in which you store the authors, a table in which you store the books, and then another table in which you connect the information together, right? But here you cannot do that. So typically what you do in a document-oriented database is that you have a document related to an author, and then within that document, you store everything. You store every information about every book that the author has written. This is called document nesting in the literature. So if you explore document-oriented databases and you come by that term, this is the meaning of document nesting. Use cases, similar of course to key value stores, but here you can manage data which is a little bit more complex. So for instance, inventory data or within a company. As for the systems here that can be used, I would say that MongoDB is the most common one. You can find it also in several companies in use. And then we come to the column family stores. Only question. What about the break that we were discussing before? How we arrange it? Sorry? Oh, yeah. Is there somebody waiting for us? Okay, maybe you can just wave an hand when I should stop. Okay. So proceed another 10 minutes, maybe. Yeah. Okay. Okay. The third family of NoSQL solutions is that of column family stores. Column family stores actually are. This is not a new concept because column family stores can be traced back to the 1970s. So back to the roots here, basically, where also relational databases were born. However, even if they were theorized in the 1970s, basically there was no need for this kind of systems in the 1970s. So they stayed just there up to the 2000s. The idea behind column family stores is as follows. A column-oriented database stores each column of each table separately in different disk locations. And the values belonging to each column are put together one after the other. Yes? You can think about Excel, but instead of an Excel storing the information row after row, you store column after column on the disk. And now we see an example. So think about a table made like this. In a classical database, in a relational database, you would store information in this manner. You can see date, store, product, customer price. So you have this row, and so on and so forth. Just think about storing this stuff on a disk. In a column-oriented database, instead, you proceed in the opposite manner. So first you store all the information regarding the first column, then all the information regarding this other column, and so on and so forth. So you proceed in the opposite way, orthogonally. This is the key intuition behind column-oriented databases. Why should you even want to do that? Well, because if you have certain kinds of operations that you want to perform on this data, then it is much more convenient to have data arranged column by column. Just think about a table, a very large table in which you have bank accounts with the money in each bank account, and you want to calculate the average amount of money. If you have the column pertaining to the money stored in this manner on the disk, then it is very easy to retrieve all the values and calculate the average. If instead you store the information row by row, it means that you have to extract all of the rows, one of the other, then get just the field of the money for each row, and then calculate the average. So it is much more immediate to perform the average here if you store the information column by column. The other nice thing is that in computer science, if you put together physically data which are similar, then you can compress them much more easily. This means that to store the same amount of information, a column-oriented database typically uses less space on the disk because it puts things which are similar together and then compresses them better. As for the downside, of course, when you insert a new tuple, a new row of information in a column-oriented database, here you have some added cost because you have to take your row, break it down into the single field, and then store each field separately. Also, if the majority of the operation that you perform reads entire rows, then this costs a little bit more than in relational databases, because you have to retrieve the single fields one after the other and then combine them together in a row and then return it. So it's a kind of trade-off here that you have to evaluate. So the difference between the let's say it really depends on the use case. If you'd better stick with a relational database or a column-oriented one. If you work on single columns, then it's better a column-oriented database. If your typical use case is working with entire rows instead, it's better to stick with a relational one. It's a matter of trade-off. And these are the most common column-oriented databases. And again, there is one of them, which is the most common one, which is Apache Cassandra. An interesting thing about Cassandra is that it gives you also a language to interact with the database, which is similar to SQL, and it is called CQL, Cassandra Query Language. But it is just a syntactic similarity. It is very poor, this language, with respect to SQL. And then we have graph databases, which I would say now are the most popular ones among NoSQL solutions. And this is because in many domains, you can represent information using a graph. So with a graph, so using nodes and edges, you can represent highly interconnected data as the ones you would find in social networks, where you have users that are interested in the sport, users that are friends of other users. But this is not the only case, because graphs can also be found in biotech applications. So molecules are basically graphs. You can find them in geospatial applications. Because also the topology of a building can be represented as a graph. You have a room which is close to another room that belongs to a floor. So again, you can represent it with a graph. Intertextuality, if you consider that classical literature, can be represented as a graph, and so on and so forth. So this is basically what happens. So within your database, you store the single node. In this case, we have a single node which represents person. Each node has some properties. In this case, we have a single one, the name of the person, Alan. And then these nodes point one to the other. You can see, for instance, using different relationships. For instance, here we have Alan, who loves Zach. Zach is friend of Alice, and so on and so forth. The most important thing here to notice is that you have to imagine this to be stored on the disk of your computer exactly in this way. So if you are here and you want to go there, you can simply follow this pointer. This is a physical pointer. If you are here on the disk, on the location of the disk of your computer, this arrow says to locate this node, you have to go in this other part of the disk and enter it. This is immediate to follow these arrows because they give you the exact locations of where this information is stored. This is very different with respect to having a relational database instead. So, of course, you could represent this graph using some tables. Can you imagine how? How would you use the tables to store this graph?
Friends, flowers.
Yeah, the idea is to decompose it in a very similar manner. Yep. So we have maybe a table that stores all the nodes. So the node of Alice, Bob, Zach, Ellen, you can see that here, right here. And then we can have several tables, one for the friend, as your colleague was saying, one for the labs, and so on and so forth. Or we could use also a single table, and here we specify the kind of relationship, and we say that Bob is friend of Zach, Zach loves Ellen, and so on and so forth. But here we have two downsides. The first is that, of course, it is way easier if I just ask you, give me all the friends of the friend of Zach. So here you can answer it maybe a little bit more easy because you can follow the arrow, reach Jim, and then follow the arrows going out from Jim to search for his friends. But here it's very difficult to answer to that query using the table. Or another query could be, give me the shortest path going from this node to this one. Here you can follow the arrows, but here in the table you have to do a very complex SQL query. This is the first downside. The second downside is that these tables here may really explode in their size. Already the tables to store this graph here can become big. And as the tables become bigger and bigger, it is more and more difficult to access the information. Because to retrieve something from a table that has millions of rows can become slow. Instead here, even if the graph becomes enormous, you simply have these very nice pointers that point directly to the different nodes. So you can always follow them at the same computational cost. Was this clear, the difference between the two manners? Okay. And as for the solutions available for graph databases, again, we have Neo4j, Allegro Graph, and somehow Neo4j is the most used right now. Okay, I think that we can make that that break that was promised, I think, till 11.
How long will be the break?
They said to me it was till 11. It was supposed to be from 10 to 11, but we split it into breaks somehow. Till 11. Okay, so right before the break, we were just finishing up with the graph databases, and I just mentioned them again because they are really being used a lot lately, and this is not a coincidence, as I was saying, because we realize that a lot of different kinds of data can be represented in this manner. And then also deep learning comes into play here because you have graph neural networks that can be used once you store the data using this convention here. So good to know. We have been talking about relational databases, and we said that they are good for some things because they make your life easier, basically. Then we have been talking about NoSQL solutions, which are the only possible thing that you can use sometimes. So if you have a lot of data or they are very heterogeneous, but they do not have SQL, then they help you less in maintaining data consistency. Then one may ask himself or herself, well, is there a kind of combination between these two solutions? Is there something that tries to put together relational databases with NoSQL? And the answer is yes, of course. And there are the so-called NewSQL approaches. The thing is, in the last years, we have been experiencing a reapproach between the two worlds of relational databases and NoSQL solutions. And the idea is to combine the performance capabilities of NoSQL on one hand with the data guarantees offered by relational databases on the other hand. And there are some examples of that. For instance, we have been, pertaining NoSQL, already mentioning that Cassandra, the column-based store, has a CQL, so a language that somehow is inspired by SQL. Then Neo4j, which is one of the graph databases that I was showing you before, has the support for the so-called transactions, and these guys here, transactions, are those that then allow you to solve those atomicity and concurrency problems that we began with them, not the bank transfer, the airline. And these transactions somehow allow you to deal with them. So somehow some NoSQL systems try to implement within them something which is typical of relational databases. On the other hand, I would say that the majority of the commercial relational databases today offer you the capability of storing not only tabular data, but also the so-called JSON-B data types, which are just binary data types that you can store within the cells of a table. So you can say, okay, I have a table, for instance, the first column is the picture name, and you write down the name of the picture. The second column is the picture itself, and within the cell, you store the binary data that composes the picture, basically. And you can do that using this kind of format. So then there are some derivations of relational databases which have explicitly been designed to deal with large quantities of data coming fast. An example is TimescaleDB. So what I want to say is that if maybe 5, 10 years ago there was this clear distinction between relational and NoSQL solutions, now these two worlds somehow are colliding. There is still distinction, but it is becoming thinner and thinner. Okay. And this is our recap. So we have been mentioning up till now structure, semi-structure, and unstructured. We've now been focusing on these two guys here. We have seen NoSQL solutions from them. We categorize NoSQL solutions into key value stores, document-oriented, column-based, and graph databases. They are very different, one to the other, but they share these commonalities. So they are distributed, meaning that they scatter the data into multiple machines typically. They offer support for the big data, but they have very simple data models. And then there is this guy here which tries to mix everything together. So relational and NoSQL together. Okay. So up to this point, we have a rather complex scenario in which we have different kinds of databases. And you may very well think that within a company, for instance, there exist several kinds of databases to store different kinds of data. And these databases can be relational, can be NoSQL. Typically, companies have both of them to solve different needs. But a company, or other than databases, for other kinds of data, maybe simply stores information on the disk as it is. Maybe they are pictures or audio materials. So what happens is that within a typical IT infrastructure, data is scattered into several different places. And this makes data analysis quite hard, because if you want to perform a very complex analysis, it might be the case that you have to retrieve something from a database, something else from another one, then to read something from the disk, and so on and so forth. And to proceed with our lecture, I want to introduce a motivating example because it will make everything much more clear. And here we find ourselves in the contact center domain. So we have these companies which basically work as a front channel for other companies. So they deal with telephone communication, but not only, they also with email communication, chat communication, and so on and so forth. And why the contact center domain? Because actually, during their operation, these kind of companies generate vast amounts of heterogeneous data. Because when they deal with the telephone conversations, they store, for instance, structured data regarding the time in which the call has been placed, the two telephone numbers which has been connected, and so on and so forth. But they also have unstructured information, for instance, the voice recordings of the phone conversations, or semi-structured information, the answers to telephone surveys, also text information, written notes, chat email messages. So you may think basically of every kind of data. In a contact center, you will find it. Just to introduce some nomenclature that is going to be used later. A contact center typically deals with three different kinds of operations. We have inbound operations, which means answering incoming traffic. This is when the contact center receives a phone call from the outworld. For instance, you are calling a toll-free number to ask something, or you write on a chat on a website, and so on and so forth. But also, contact center may produce outbound operations, which are the annoying ones, which is when they call on your phone to say, hey, I want to sell you something. These are outbound. And then there are also back office operations, which do not involve any exchange with the outside world, but back office means to prepare data to be used here or for analysis. So inbound, outbound, back office, these are the three things that a contact center does. Originally, contact centers were all born as call centers. So originally they just dealt with telephone conversations, but over time they began to deal with emails, chats, and everything. So this means that their information infrastructure is typically quite complex and heterogeneous, because as the company dealt with more and more media of communication, for instance, they expanded their information infrastructure to make it possible. So this is a typical situation that you can find in a contact center. It is inspired from a real world situation that we studied a couple of years ago. We can start within this diagram from here. So here we have the contact center employee. And this employee works by answering or performing phone calls, exchanging messages, and so on and so forth. And in doing that, he or she generates several streams of data. Some of them are structured. We have mentioned them, for instance, the technical data about the phone call. So the call numbers, the duration of the call. These are just tabular data that can be stored within relational databases. But then maybe these phone calls, for instance, are made to get answers from a phone survey, and then you might have a NoSQL database to store the answers made to the survey. But then you might have the voice recordings of the phone calls. You might have some free text annotation that the person takes while answering the calls, and you store them on disk. So what used to happen within this company is that there was no single central point which could back up the analysis tasks. Every kind of analysis task, but also the billing tasks made for the customers, and all these kind of activities had somehow to keep into account this very heterogeneous set of systems and retrieve information from all these systems separately and then combine them somehow. Which is not very convenient, of course, because heterogeneous systems require ad hoc solutions for reading and writing data. You would use SQL towards a relational database, but then you have to use a different kind of approach for the NoSQL ones. Then also different kind of databases usually adopt different conventions or formats for storing the data. Think again about the phone number. Maybe in one database, it is stored as two different fields, prefix and phone number. And instead, in another database, it's stored as a whole, as a single number, which already complicates things. If you have a lot of databases, again, it means that probably the same information is stored into several databases. And this is bad. We have already seen it for data consistency. And then there is this point here, which still we haven't mentioned. Classical databases, as the ones that we have seen up to now, think about relational databases for now, which might be a little bit easier. Those kind of databases are typically designed to deal with daily operations. So those kind of operations that you perform day by day when running your company. So if you are a bank, then your database, typically the operations that it will support are going to be bank transfers, bank withdrawals, the person that accesses the bank from their smartphone and changes something, those kind of stuff, daily operations. You can see that this kind of operations, typically the single operation deals with very small quantities of data, maybe the single bank accounts, and they are very detailed because you want to modify something on a specific bank account. These kind of operations, which are daily routinary operations, they do not involve a lot of data and are very detailed, are called online transaction processing, or LTP. These are the kinds of operations that classical databases support. Instead, when you perform analysis, you are interested into a whole different kind of operations, because when you perform strategical analysis, you want typically to read great amounts of data and then somehow aggregate them to obtain the mean, the average, or something, or a trend. So you're dealing with big quantities of data, but you are reasoning at a more abstract level. You are not so detailed in the data. You are not looking typically at a single bank account, let's say, but you consider maybe the average of all the bank accounts. So keep also this in mind. These systems, which were present in the previous picture, were designed to perform this kind of operations, daily operations. So there are several issues that somehow hinder our capacity of performing analysis over the data. And first of all, there is a necessity of having a clear and uniform view over all the data owned by the company. You want to have a single repository, a single physical place in which all the data is there, all the data you need to perform the analysis tasks. And this repository, other than combining within it all the data that you need in a single place, must be designed specifically to support analysis. So not to support those OLTP, online transaction processing stuff, but online analytical processing. So here you want to perform operations that aggregate together a lot of data to perform to gain strategic knowledge. And there is a technology, fortunately, that you can use to do that. And this technology is called data warehousing. Data warehousing was born, I would say, at the beginning of the 1990s, historically. And contrary to NoSQL, here we have a clear definition of what data warehousing is. And this definition is by William Inman, which is one of the inventors of data warehousing, who says that a data warehouse is a subject-oriented, integrated, consistent, non-volatile, and time-variant collection of data in support of management decisions. And this is one of those definitions that you find in your career in which every single word is important. If you remove just a single word from this definition is not correct anymore. Every single character that you see there is equally important. And we are going next to split this definition into the subpart and see what this means. Just to give you intuition for now, we've already been saying that, but let us remark it. The data warehouse will serve as a single integrated source of truth for all your analysis tasks. And what happens is that this data repository poses at the heart of the so-called decision support system, which is a system that informs the managers of the company about what is going on, basically, to take actions, to take decisions. So let us see what the definition means now, breaking it term by term. So the first part is subject-oriented. So a data warehouse focuses on enterprise-specific concepts. So it means that a data warehouse talks about concepts that are present in your domain of interest. So if you are in the insurance domain, within a data warehouse, you may find tables, let us say, and a table may be called customer, another agent, policy, claim, accident. You will find all these terms within your data warehouse. You may say now, also in a classical relational database, I find these tables here. So why the situation is different here in the warehouse? While it is true that in a classical database you find this, other than this stuff, in a classical database, you find also a lot of other tables that are there just to support those daily operations. So maybe there is the software that you use here to connect to your bank account, and the software needs some technical information regarding your account, regarding your profile, and so on and so forth to work. And then you also have to store those kind of data within the database. if you want to make your application work. So this means that these data, which are very relevant for your analysis tasks, are contaminated by a lot of other data which are there just for technical reasons, to make things work, to make your applications work. Instead, in a data warehouse, you just bring these data which are relevant for analysis tasks. You do not bring those technical stuff which you are not interested in. If you want to distinguish, you can say that a data warehouse focuses on enterprise-specific concepts, and instead, a classical database relies on enterprise-specific applications because it had to provide support to those applications, not to analytical tasks. Is this clear, this difference between the two systems? Okay. So subset-oriented. The second term that we encountered is integrated and consistent. So the data warehouse poses at the heart, we said, of the information system of the company. And so it is fed from multiple disparate sources. All the information that is stored within the warehouse comes from other systems, other databases. We said that different databases may adopt different conventions to store the data. And so when you bring the information within the warehouse, there is the need to convert this data in a uniform format. So when you define your data warehouse, you say, okay, the format for my data is as follows. Then when I bring the information from the other sources, I convert this information to this format, to exactly this shape. Just for some examples, the most trivial ones, if in my data warehouse, I decide that the phone number should be stored as a whole, then if another system stores the phone number as prefix and suffix, I have to merge them before bringing them. This is a thing, but then other things that you do are also data cleansing, because when you bring something into the warehouse, this is the moment in time when you see that maybe you have the same information scattered into multiple systems. So when you bring them information, maybe now you see that you have the same customer into two different databases. And this is the moment when you have to deal with possible inconsistencies, understand which of the two databases have the truthful information, let's say. Of course, this data loading phase into data warehouse happens initially as a bulk load when you first develop the data warehouse, you bring everything there. But then the warehouse must be kept aligned with what happens in the original systems. So let's say that every hour you bring in the new information. Meaning that the warehouse is not going to substitute the original systems. The original systems, the original databases will always be there to support the daily operations, those OLTP stubs. But then you have the warehouse that also brings everything together. You will have both of them. Okay, so this phase here that brings the information within the data warehouse is called extract, transform, and load in the literature, ETL. And it is a very complex and very expensive phase in terms of time, but also money. So there is a so-called data quality process by which you try to understand up to which extent to clean, to integrate the data. So the bottom line is that everyone would like to have all the data clean as possible within the data warehouse, but sometimes this is simply unfeasible sometimes because it would cost too much. The important thing to know is what I'm bringing into the warehouse, which kinds of data I'm sure are clean, are consistent, which other kind of data instead might be not so consistent, and up to which extent can they be not consistent, so that I can consider it when performing analysis. In every case, you should try to clean and to integrate data as much as you can, because of course, if you perform analysis and these analyses are based on data which is wrong, even if your analysis is the perfect one, you will get wrong results, of course. This is the concept of garbage in equals garbage out. Okay, non-volatile. This is another characteristic coming from the definition of warehouse, and it means that once you insert something in a data warehouse, this data is neither changed nor removed. Once you get something there, it will stay there. This is very different with respect to a classical database. In a classical database, think about the bank account again. You have the total amount of money of your bank account, then a bank transfer arrives, your amount of money increases, but the previous situation is not there anymore. Maybe you can recover it rolling back all the movements, but the previous situation is not there, you have to reconstruct it. Instead, in a data warehouse, everything is kept there, always. It's like taking a successive series of snapshots. It's like taking pictures. So you have a picture situation that a change happens, you take another picture, and so on and so forth. You can always roll back these pictures. So data warehouses can be viewed as read-only databases, which is, again, rather different with respect to classical databases. And this part of the definition here, the non-volatile part, brings you also to the time variant part of the definition, meaning that within the warehouse, you can easily see the data as it existed at many points of time in the past. So at any instant, you can say, how was my bank account 10 years ago? And you can get the snapshot without tracing back all the changes up to 10 years ago, which would cost a lot of time and would be inconvenient. Yep.
So is it possible to remove the data change, or is it completely impossible?
To remove that, sorry?
Is it possible to remove the data once you put it in or change it, or is it completely impossible? Because you said it's not changed, not removed.
Yeah.
Is it possible?
It is possible, and maybe you do that if you realize that you have inserted something which is wrong, and so you correct it. Let's say that it is possible if you want to do that on purpose, to correct something. But the usual way in which new data comes to the warehouse, the usual way is not to perform changes. You make these changes only on purpose. It's clear? Okay. The idea is as follows. Okay. Let us say you have this bank account, no? With your amount of money. Then you receive money, you send money, and so forth. This stuff is brought to the warehouse once in a while from the original system, and then you get all these snapshots of your bank account. And here you are not modifying anything basically because you are adding new snapshots. At a certain point, for some reason, you see that you had an error in the original system, and you had 10,000 euros more right from the beginning in your bank account. So what you can do is modify each of these snapshots, adding 10,000 euros to each of them to correct for that error.
It will take a long time, yeah.
Yes. and it will take a long time, and not only, but it is very easy to make a nightmare if you do that, because modifying things afterwards in the warehouse is always difficult due to this very complicated stuff regarding the time.
Okay, good. Thank you.
Thank you. Okay, so this is another thing. So we have this history of changes in the warehouse, which is always good to have if you want to perform data analysis. We have been talking about OLAP and OLTP already, but just to remark it again, classical database OLTP application. So you modify or you read small pieces of highly detailed data. So for instance, you perform a bank transfer from one account to the other. OLAP operation instead are typically read-only operations because they are made to perform analysis, which aggregate historical data over large data sets. For instance, an OLAP operation would be calculate the average amount of money that customers under the age of 20 withdrew in Italy in the years 2018-2022. To do this in a classical database, this would cost you quite a lot of time also to perform this kind of query. Instead, in a data warehouse, we use the so-called multidimensional model, which is a very specific way to arrange the data, which is intended to answer to this kind of queries. Okay, another couple of definitions. Before proceeding further, we have been talking about the data warehouse as this single point of truth within your company where you bring all the data there. There is another concept, which is that of data mart. The fact is that the data warehouse may become very big, may contain a lot of different data, and your company might have different departments, let's say, maybe the research and development department, the marketing department, and so on and so forth. And of course, not all of the departments are interested into all of the data. So just to make things a little bit more convenient to them, you may want to define smaller databases, which are like smaller subset of the data warehouse that just contain the data which is of interest for one of the departments, which is useful, first of all, because assessing a database which is smaller is faster. And second of all, it might be that different departments prefer different ways to arrange the data. So here you can use slightly different conventions than the ones that maybe apply here to the data. But still, this is easy to do because at least you start from a uniform representation and you transform the data as you wish later. And this is the overall picture of the entire process. So you have your original systems here, your original data sources. Then you have the so-called ETL process, extract, transform, load, that brings this data together, combines them, cleans them, integrates them, and then loads them into the warehouse. And then in the warehouse, which may also be another data mart, you can perform your analysis tasks. There is also here this other database, this metadata database, which is which serves a very specific purpose. So let us say that you have your warehouse. At a certain point, performing the analysis, you discover an issue in your data. You couldn't see that before because the data was scattered and it was impossible. But now that you have the warehouse, you discover something which is wrong here. And you want to trace back where the problem was here. The metadata database here allows you to do that because typically in a warehouse, for every piece of information, you keep track of where that piece of information came from. This is called data lineage. So keeping track of the original sources of the data so that you can always trace back, for instance, the origins of the problem. And it happens quite a lot, especially at the beginning when you first define a data warehouse. Okay, we have been talking about the data warehouse. The last concept we should add is that of data lake now. Remember how a data warehouse works. So we define our schema, all the data, and then regularly, maybe once every hour, we bring the data there, we transform the data to bring them there, and then when we want, we perform analysis of the data there. This approach is called schema on write, because it means that when data are brought into the warehouse, it's like I'm applying a schema to this data. I'm modifying them to conform to a schema. The data lake takes the opposite approach. The data lake is again a centralized repository of data, but within a data lake, I store the data as they were in the original systems. So I do not perform any kind of conversion to this data, but they are stored in their native format. Together with the data that are stored in the lake, I also store some kind of metadata to keep track of how I should interpret this data, what were the conventions in the original systems used, for instance, but the data are kept as they are. It is still useful to have a data lake, although the data are kept as they were, because at least I have a single physical point which I can connect to when I want to read something. But if the data is stored as they are, it means that they have to be integrated, cleaned, made uniform at the moment in which I want to perform the analysis. So not at the moment when I write them to the lakehouse, but when I read them, I have somehow to read them consistently. And this is called a schema read, which is an opposite approach with respect to the warehouse. Well, you can see that there are two very different approaches, and we should say that a data lake is not a substitute for a data warehouse. Because the warehouse will always be much more easier to interact with because the data are already in the correct format. But still, the data lake might be useful in some scenarios. For instance, let us say that you have a new source of data in your company, and you already have a data warehouse, but the warehouse still cannot accommodate this data because you still have to expand the schema of the warehouse to do that. So meanwhile, maybe you transfer all the data to a data lake, you deal with the data lake. When you're ready, you bring everything in the warehouse. So it can be a kind of intermediate step between the original systems and the warehouse if you want. Yeah, so this is basically everything to say behind the data lake, I would say. Okay, then we have the multinational model, but I think that we can make a short break because this is going to be a little bit cumbersome.
How much?
Do you have other breaks planned already? So otherwise, we make till -10. So till 11:50. Okay. Okay. We are about to our last part. So let us go back and have a look again at this slide here. Remember that we said that classical databases work with OLTP stuff. Whereas data warehouses work with all kind of queries. So here we said you're interested into aggregating very large quantities of data together, get some insights. Think about a classical database and how it typically stores information. Maybe a database about customers, products, and orders. So you have a table regarding customers, another table regarding products, another table that is called orders that says this customer has both this kind of products. And then you might have a lot of other tables around that store different kinds of information about all these transactions. The thing is, in a classical database, if you want to perform this kind of operations that look at a lot of data and aggregate them, it means that you have to combine several tables together. You have to perform a lot of join operations. And these operations are very costly. As the table grows, to perform a join, you remember that you combine every row with every other row. That can explode, basically. And so data warehouses use a specific way to arrange the data, which is called multidimensional model, that now we are going to see very briefly. So basically the idea is having a multidimensional representation of the data, and you obtain this representation of the data by performing some pre-aggregations on this data. So the idea is, when you perform analysis, you do not start from the single bit of raw data, the single pieces of raw data, but you start from something which is already pre-aggregated to some extent. So you start from something which is in the middle ground, let's say. What happens in the multidimensional model is that we use these three different concepts to arrange the data. The concept of fact, measure, and dimension. These are the three concepts. A fact is just a part of your data that tells you that a specific event or a specific transaction has happened. So a fact might be the sale of the product, or receiving a shipment, or writing down a new annotation for a call. A fact, something, an event. A fact, so this event is typically described by multiple measures. Measures are numerical quantities. For example, a fact might be receiving an order for some shoes, and this fact, this event, is then detailed by two numerical measures: the price and the quantity. So how many shoes have been ordered and what is the total amount of that order. So this may be a fact and measures. Then we have dimensions. Dimensions give you a way to label these facts, to categorize them, to index them. For instance, you may want to label a fact attaching to it a spatial dimension, a temporal dimension. So for instance, that order about the shoes has been performed yesterday at the store in Trieste. This can be a dimension. So the dimension is just a label that you attach to a fact to say where, when, or other stuff, which customer. So the previous order regarding the shoes, which I remember it was composed of these two measures, so the total amount and the quantity purchased, may be labeled, let's say, by three dimensions. One which is temporal, that says it has been placed yesterday at 2 p.m. One which is spatial, served by our store in New York. and then another dimension pertaining to the customer who has placed it. So it's like having these three labels attached. Okay, all right, for fact, measure, and dimension. Okay. This slide here is always a nightmare, but I haven't been capable of writing it anyway easier. But with the following ones, it will be easier actually. So in the multidimensional model, all the data is represented within a cube or hypercube if you talk about more than 3 dimensions. In these cubes, dimensions correspond to the edges of the cube, and the facts are the cells of the cube. And we are now going to see what this means, because the most simple case of a hypercube is that we have in 2 dimensions. In 2 dimensions, we have pivot tables that you can find also in Excel. So here you have 2 different dimensions. You have a dimension which is a spatial one here, the countries, and another dimension which is the product dimension, which is here. You can see that at the intersection of these 2 dimensions, we have the numbers. And these numbers are in this case, the amount of products that have been sold. So for instance, we know that in Australia, we have been selling 20,000 apples. We know that in France, we have been selling 36,000 bananas. So here, again, 2 dimensions, place and product. We have a single measure because we have a single number, the amount. And the facts basically are the amount of products sold in each country. What can we observe here? In some cells, we do not have any value, which is possible because maybe our company simply doesn't sell for some reason beans in Canada, so there is no reason to put a number there. Another thing that we can notice is what I was saying before. These are already some pre-aggregated information. Right, here we already performed some aggregation. Maybe in the original databases, we had the single rows of the single orders, and here we do not see those single rows anymore, but we are already aggregating information according to country and product. And why this is convenient? Well, because if I want to know how many oranges I have sold, I can already start from this pre-aggregated information and just, for instance, sum this column. Or if I want to know how many products I've sold in Germany, the same over the row. Notice this thing. If I have this table here, I can always move to a coarser level of detail if you want. Maybe I want to talk about continents instead of countries. I can move together the rows. But of course, I cannot split them further. So there is always a maximum resolution, if you want, at which you can see information. So this is a pivot table, 2 dimensions. If we move to 3 dimensions, we get proper cubes. And here we have the dimension of the city, so spatial dimension. Here dimension, which is a temporal one, the quarter of the year. And here the product. So here we know, for instance, that in Paris, in the first quarter of the year, we have been selling 21 units of beverages. It's similar to the previous example, but in 3 dimensions. Again, we are just using a single measure here, the quantity sold. If you had more than one measure, in each cell, you would have more than one number, basically. One number for each measure. Remember that in the case of the pivot table, the 2-dimensional one, I told you that, well, we have the information by country, but we can combine the rows together and go up at a coarser level of detail. And this is exemplified by the concept of hierarchy. The idea is that to each dimension, I can attach a hierarchy. For instance, in the temporal dimension, I can talk about days, months, quarters, semester, years, so I can move at different levels of details. The same along the product dimension, I can move from product to categories of product. Customer, single customer, customers group by city, by state, country. Of course, choosing the dimension hierarchies is tightly linked to the kind of analysis you want to perform, because again, if I choose to represent at maximum level of detail my information by product, quarter, and stage, I cannot go down here. I cannot split the rows anymore. I can only go up for the maximum level of detail that I envisioned at the beginning. Okay, so we now have these cubes, and also with the help of these hierarchies, I can perform these 4 kinds of operations mainly. And these are the roll up, drill down, slice and dice, and then the pivot operation. The roll up is the one that we have already been envisioning. So let us say that I have this cube here with the city, quarter, and product here, and I want to look at the data at a coarser level of detail. So for instance, I want to look at the data at the level of detail of country, not city anymore. So here I group together the cities to get Germany and France, and you can see that here we have been selling 33 units of beverages in the first quarter in France, and this of course comes from 21 plus 12, so Lyon plus Paris. So we just combine together the values. And the same holds for Germany. Here we have 57, which was the 33 plus 24, right? Of course, this game of moving up along the dimension requires your measures to be additive, we say. The sum is a kind of additive measure. I can always do that, this trick. If I have something else, for instance, the median, in other words, sorry, here we have the sum of units sold, right? In this cell here. So we can always combine together these numbers using one. If here, instead of having the sum of units sold, I had the median of units sold, it wouldn't be possible to combine them to go up. I cannot obtain a coarser median from 2 medians. It's not possible. It's not an additive measure, that is to say. It works with the sum, it works with the maximum, because if I have here the maximum number of units sold in Paris and the maximum number of units sold in Lyon, I can combine them together, making the maximum of the maximums, but it doesn't work for the operations. Let us say the result sum. We have seen the roll up, then we have the drill down operation, which is the opposite. So here we have the data arranged by quarter. I can split this data at the level of months, for instance, getting the situation on the right. And if you notice, here we are in the first quarter, beverages in Paris, 21. Of course, 6 plus 8 plus 7 is 21. So here we just split the information. Then we have this slice and dice, which means that I fix some values along the dimensions. So for instance, I want to visualize a subset of the cube, selecting just Lyon and Paris here on this dimension, and selecting just the first 2 quarters here, and obtain a smaller cubes. And finally, this is the last operation. So we have our initial cube that shows you the data in a very specific manner, and specifically here for each city, you can see for each city, we are looking at the data in terms of time and product. For each city, time and product, right? If I rotate the cube, as I had it in my hands, just rotating it, I'm looking at the same data from another perspective, because here I'm saying for each product, look at the data in terms of city and time. So I simply rotated it. The data are the same, really, just the cube rotated. So for instance, you can see that 24 here we had in column as ended up here. Why doing that? Well, because some kind of patterns are more clearly visible from a certain perspective than another. And the hypercubes and the pivot tables that I've been showing you, you can consider them as a kind of intuitive representation of how the data are pre-aggregated within these systems. But then it is not that typically you have graphically this cube in front of you and you rotate it with your mouse. It doesn't typically work like that. But there are some kind of visualizations that can read the data which are on the cube and providing you a more comfortable visualization. For instance, here we are looking at, let us say, the number of sales. Of course, darker color means more sales. From a spatial temporal perspective, spatial perspective because we have this map, and temporal perspective because we also have this slider here. So what is happening here? First of all, here we have a kind of slice and dice operation here performed on temporal dimension because we are selecting a subset of the values. And here, what we are doing from here to here is performing the drill down operation. We are moving from the country level to the county level, I will say here on the right. So this is what happens graphically if you have the support of one of these cubes. And having those cubes, you can obtain these visualizations in real time. If you move this slider or you zoom in and out, you can see this situation change instantaneously because you do not have to perform so many operations to get this data because you have these cubes that pre-aggregate those data. So remember our initial situation at the contact center, which was this kind of very convoluted stuff. After the introduction of a data warehouse, you can get to this situation in which you have all the original systems, you are the interface that brings everything to a single place, and then all of the analysis tasks are chained point to this single source of information, which is also from a graphical point of view, it seems much better than before. Okay, so questions, this part? Okay. Okay, then we have our last part because for now we have been talking about which kinds of data do we have, how we store them. At a certain point, we realize that we need the data warehouses to put some order among our data. But at a certain point, we must do something with our data. Otherwise, if we do not do anything, then there was no reason in doing all of this stuff. And what we want to do is to extract value from the data. And this is called data monetization in the literature. Of course, monetizing from the data doesn't come just from analysis, but of course, there are some companies that have made just a business to sell the data as they are, which is, for instance, data in social networks. For what concerns us, however, if you want to focus on analysis, there are three different kinds of analysis that you can perform on your data once you have them arranged, as in the previous slides. So we have descriptive analytics, predictive analytics, and prescriptive analytics. Descriptive analytics is the most simple kind of analysis that you can perform on your data, and almost every company employs it, and it is also called business intelligence. So in descriptive analytics, you typically focus on historical or current data, and this kind of analysis make use of all-up cubes as they are. Think about the example of the map before. We were just looking at some situation in the past of the sales. So in descriptive analytics, it is called like that because basically it describes what happened or what is happening now. So typical questions that you can answer using this kind of analysis are: how many customers we lost to the competition last year? Or what customers are likely to be committing a fraud currently? Because this can be rephrased as which customers are currently deviating from their past behavior. So this is descriptive analytics, past or present. Then we have predictive analytics, in which you look at the past, but with the idea of building some models to provide you with a vision of the future as it will be probably like. This is called also business analytics. So business analytics heavily relies on statistical analysis. It relies on machine learning to try to forecast the future based on the past. So typical questions here are: what will the churn rate of my customers be in the next years? Or what customers are likely to be committing a fraud in the next months? And our last step is that of predictive analytics, prescriptive, analytics instead. Here, we do not just provide a vision of the future, as in predictive, but a prescriptive analysis framework can also suggest to the decision makers how to reach some future goals. So you can envision some future that you want to obtain, and then you can also build which steps to follow in order to reach that future objective. So for instance, within a prescriptive analytics framework, you may ask yourself, what are the factors that mostly influence the probability of churn, so of my customers leaving? And then you may ask yourself, if I tune these parameters, how will I end up in the future with a churn rate? This kind of analytics is rather recent, and still I would say not the majority of the companies use it. But I can also give you an example of this kind of prescriptive analytics in our contact center domain. So remember that we left our contact center with the development of the data warehouse, which was at the heart of the new information infrastructure of the company. So we had this nice information infrastructure, a decision support system, basically, which could give to the managers all the information to take actions in a much more easier manner. But an evolution of a decision support system is the so-called decision management system, which is an information system that doesn't only provide information to the managers, but it is also capable of taking some actions, some choices on its own. And how can it do that? Maybe based on some domain rules or based on some machine learning models, with the idea that the decision system should take all those actions which are routinary, which do not require managers to take very strategic decisions. So to leave the managers free to concentrate on strategic actions. What is a possible example? So let us say that we have our initial systems in our contact center that track, for instance, the number of phone calls going out and in the call center. Then we have our analysis within our infrastructure. And we developed a model that somehow forecasts how many phone calls we will receive for a certain phone number, for a certain service that we are providing. At a certain point, our model forecasts that we are going to receive a lot of phone calls in the next hour. And so the system might autonomously move some of the employees of the call center from answering the phone calls of a service to that of that other service. So to increase the number of customers of employees dedicated to that service that is going to receive a lot of calls. This is a kind of automatic action that could be performed. Another one might be in the industrial domain, that of having some models that read the telemetry information of machinery and autonomously decide when to schedule some maintenance operations for the machinery. So this is our last recap, I would say. We said that we have many sources of information, and those analyses are difficult. So we need a centralized repository of data to perform this analysis. And we have two different but complementary solutions. We have the data warehouse on the one hand, which is subject-oriented, integrated, consistent, non-volatile, and invariant. And we have, on the other hand, data lake, which, remember, has the schema read approach, which is rather different than the schema on write of the data warehouse. They typically are at the center of a decision support system within a company. And this decision support system typically deals with these two kinds of analytics, descriptive and predictive ones. If you incorporate prescriptive analytics, you are likely to end up instead with the decision management system, which is this more advanced instrument that you can have. And this is the recap of the recap. So we basically covered a lot of stuff today. So we started saying that data management is very complex. We have several kinds of data, structured, semi-structured, non-structured. Then we have also some data which are very recent that exhibit some specific properties of volume, variety, and velocity, which are the big data. Fortunately, we have database management systems that allow us to deal with those data, and depending on the kind of data that you have, you may rely on relational NoSQL or new SQL databases, but the choice is not so easy. The fact is that typically you end up with many systems, so you need data warehouses to perform data monetization. And this is just some bibliography notes if you are interested into this kind of stuff to focus more deeply on these topics. And I would say that this is all for today.
On introduction. With this lesson on introduction to the industrial cybersecurity, my name is Miguel Ángel Prada. I'm from the University of León in Spain. Well, the contents of this presentation will be the following. First, we will review some concepts either from cybersecurity or from industrial control systems that we need to know in order to understand the relevance and topics related to industrial cybersecurity. After that, we will try to explain why this topic is important nowadays. First of all, it will be important because of the relevance and the criticality of industrial control systems in the operation of our society, but also because of the distinctive features that industrial control systems have when compared to typical information systems. That's the following point that we will review. And after that, we will try to see the different parts, the different elements that let us assess the risk that our system has from a point of view of cybersecurity. We will review the most important incidents that have happened in the last years. And finally, we will try to discuss some choices we have to avoid or to mitigate the security risks that we have in these systems. Obviously, both from the point of view of threats, vulnerabilities, and security measures, we will just use some examples because it will be very difficult to make a comprehensive list of threats, vulnerabilities, or measures. Anyway, well, if you have a question or a problem, please let me know. Well, the first idea that we need to understand is that in the context of this presentation, we will use the idea of industrial process as any process meant to obtain, transform, or transport primary products. That process will, in the context of this presentation, will be usually something that happens in an industrial facility. But it could be extended to a more general concept because, as we will see, industrial control systems are not only found in a factory, in an industry, but they can also be found in critical infrastructures or in other objects or elements that we use in our daily life. Anyway, any industrial process will use some kind of automation, some kind of equipment and techniques to avoid the need of constant human intervention. And this automation will be structured in the shape of a control system or an industrial control system. That will be the system that decides how we actuate over the physical elements in order to maintain that process in control. Nowadays, these industrial processes, these industrial control systems can be understood as cyber-physical systems because not only the physical part is important, it's also very important both the communications and the computing, the information part of the system. As a result, since we rely so strongly on computing and communications, cybersecurity becomes a problem. And we will not only need to defend our systems from accidental situations, but also from intentional attacks. As we will see later, in English we have different words for these accidental and intentional problems. In one case, It is safety, and the other case is security. And we will focus on security, and we will see that for a long time, the theory, the technologies in industrial control systems have been only focused on safety, only focused on the protection against accidental incidents. Well, when we are talking about cybersecurity, we need to know that a complete security is impossible, and we need to just do a risk management. We need to understand which are the more important risks and try to mitigate them as much as possible using different technologies or limiting the exposure of some of the technologies. The idea of risk from a formal point of view is the likelihood of an undesired event. In this case, this undesired event is an intentional attack, multiplied by the impact this event will have in our systems. The likelihood of an undesired event will depend on the threats, that is the different agents that are willing to attack our system, the vulnerabilities that our assets have, and the countermeasures that we use to mitigate those threats and vulnerabilities. And well, in the end, in the case of cybersecurity, in general, not only in industrial cybersecurity, everything revolves about three different concepts: confidentiality, integrity, and availability. The idea that we need to defend our systems from an attacker being able to see our private information, that would be confidentiality. Try to avoid that our messages or files are modified without not knowing them. That would be integrity, and letting our systems work, operate all the time. That would be availability. We will see that in the case of the industrial cybersecurity, the most important point will be availability. Anyway, why it is important to speak about this topic? Why industrial cybersecurity is so relevant? Well, first of all, because industrial control systems are essentially everywhere, not only in factories, not only in industrial facilities, but also in big buildings that have automated their heating, ventilation, and air conditioning, or the lighting. These control systems are the ones that make a car or any means of transport work, and are beginning to be present in more other objects, given this IoT, this Internet of Things, or Industrial Internet of Things movement, where we are trying to make everything smart, in the sense that it has the ability to measure data from the environment to work in a smarter way, but sometimes it will also have this action over the physical world that can be a very important impact. And above all, there's another sector where control systems are very relevant, and that's the sector of the critical infrastructures. Critical infrastructures are the systems that support essential services in a society. We are thinking about healthcare, transportation systems, energy supply, water supply, etc. In some cases, for instance, energy supply, water supply, transportation systems, they rely strongly on control systems that are essentially the same as the systems that we have in factories, except for the use of maybe different technologies or different industrial communication protocols. But in the end, the idea, the architecture, and the features of those technologies are essentially the same. Well, obviously, those critical infrastructures are very important for a society and need to be defended. And in this case, we have, from the last 10 years, let's say, laws and regulations that are of compulsory application. But we'll see that other applications of industrial control systems are not yet as regulated, but can be also very critical. And the problem is that we don't have such a strong culture of cybersecurity as in the most general information systems, in the more general IT world. And that's because industrial control systems have some important differences, and it's a field that has grown separately from IT from a long time. In the case of industrial control systems, we have two important ideas. First of all, that industrial facilities are usually places where everything has some procedures to follow. And for a long time, there were no procedures for cybersecurity. And as a result, the workers of these facilities understood that if there was no procedure, it was unimportant. There were a lot of procedures for safety, for the protection against accidental events, that has always been considered important in control systems. Essentially, avoiding that the damages, the natural disasters or the failures in equipment could cause damages in our facilities or in the people operating them. In some cases, depending on the criticality of the systems, we also had a strong culture of security, of physical security. The idea of having fence, doors, security staff that avoided theft or sabotage of our systems. But there were no regulations nor standards about cybersecurity, about the security of the data or security of the systems, of the information and communication systems. And well, that was due to different aspects. First of all, that in the beginning, the very beginning of these systems, they were designed to work in an isolated way. And it was real that there was an air gap. Usually the people in the English world refers to this idea that the systems were isolated, and as a result, the risk of a cybersecurity problem was low. But that was soon false, because due to the advances in communications and information systems, the creation of the internet, and the fast improvement of the technologies, connections from the corporate network of for a company or facility to the industrial park were created. Staff that was working remotely needed to have connections to the system for maintenance or to be able to monitor what was going on. And in the end, this air gap was disappeared completely. But the staff who was untrained on cybersecurity still thought that they were protected, that they were doing something so difficult and so different to anything else that nobody from the outside will know how to use their systems to cause damage. They had this idea of security by obscurity that is a very bad concept that was known in IT for a long time. That was not the way to do. They thought that if something was, some technology was obscure, was not correctly documented, the attacker wouldn't know how to use it. But that's not like that. The attacker might learn how to use it, and if the technology is obscure, you won't be able so easily to understand, to monitor the movements of your attacker. Anyway, there was a convergence in any real industrial control system that is working today. There will be off-the-shelf software that is commonly found in other corporate networks. There will be information and tools available either legally or illegally, and as a result, anyone can learn how to use our systems. And well, we need to be aware of that. Well, the idea is that then we have had these different cultures. One would be IT, information technologies, and the other one would be this industrial world that is usually called also OT, as a contrast, meaning operational technologies. We don't have such a developed culture and technologies in that sense, in this sense, and we don't have such a well-trained staff for that matter. So, well, we will see that it has been a point of concern for governments, manufacturers, operators of industrial facilities. And in the last years, there has been a lot of efforts to well, in some way, reduce this gap and have at least a situation as good or not as bad as we have in other information systems. But anyway, we can say that the lower of maturity of the technologies, procedures, and staff is lower. And that's not only due to these, well, historical reasons, but also due to some specific differences that we have in industrial control systems. And we will try to review them in this part of the presentation. First of all, we need to understand that in an industrial control system, unlike a typical information system, is designed to be working for maybe decades, for maybe 20 or 30 years. And that will result in some technologies becoming obsolete because obviously the technologies advance much faster than this lifespan that we are saying. On the other hand, industrial control systems are usually designed, or in most cases designed, to be working continuously, sometimes 24 hours a day, 7 days a week. And as a result, it's not possible to continuously update the systems as we do nowadays with the operating systems in our offices or at homes. Furthermore, we were talking before about confidentiality, integrity, and availability, and we said that availability is the most important point in the case of industrial control systems. Availability means that our system needs to be working as it was designed to. And anything that we do, including patching the system or updating some of its parts, might result on the system failing to operate correctly. And that's the reason why maintenance, patching, and updating the system is complicated. But also, we have another problem, and that is that most of the well-known security tools are tools that are active, that are disruptive, and they can complicate the normal operation of the system. We are thinking about antivirus, about vulnerability scans, etc. And well, that means that we won't be able to translate easily some of the main concepts of cybersecurity, of general cybersecurity to industrial cybersecurity. There are some things like updating or patching that won't be done easily. There will be some tools that we will need to adapt. On the other hand, we will also have some technologies that might be very basic from a point of view of security, but that are very well optimized to provide low latencies or determinism or real time. In these cases, we are facing specific communication protocols that are completely different to the protocols, the communication protocols that we find in let's say, a corporate network. And these communication protocols won't be so focused on security features as the common protocols, let's say HTTPS or the protocols that we use for email and so on are. They will be, and we will see that that's one of the main problems, very simplistic, and they will lack any kind of encryption, integrity check, or authentication in most cases. We will also use some elements, some devices that are specific and that are, again, designed to make their task very proficiently, but won't have a lot of computational resources, and we won't be able to add countermeasures inside of these devices. Furthermore, it will be difficult to introduce changes, disable services, or add additional software to the provider setup because it might break availability, and because we will have a variety of manufacturers and technologies, and everything becomes more complicated. We won't also be able to monitor what's going on inside of these devices, because, for instance, logs might be only obtained through the manufacturer tools, and as a result, some kind of security monitoring or forensic analysis after an incident becomes very difficult. And then we need to adapt to the needs of the industrial control system itself. Well, operational technology staff will have some needs. We might have specific or very large network architectures. Maybe the cybersecurity staff needs something that is somehow in some kind of competition with what the operation technology staff wants. So in the end, it becomes different. And also we need to understand that IT and OT staff will have not only the different priorities, but probably different training, and as a result, different language. So well, we will see that one of the most important things that we need to do in this context is to train the staff and to raise awareness of the problems and of the potential impact of a cyber attack. Well, what are the rest of distinctive features that we have? We said before that sometimes we have different technologies from different manufacturers, and that's the case that in industrial control systems sometimes we depend a lot on the manufacturer or on the integrator that has designed and installed the system and that maintains it. Not all the time, except for big companies, usually the design, development, and maintenance of the industrial control system is done by a third party, and as a result, we have a bigger dependence in that sense. And well, finally, maybe the most important difference of industrial control systems with respect to information technologies is that the impact of cybersecurity incidents in the field of industrial control systems are much worse than in the case of information technology, because we will have the same impacts that we have in information technology, reputation, economic impacts, but we will also have physical impacts, because the industrial control systems act over the real world, and well, that might cause the damage of our infrastructures, might kill people, damage the environment, and obviously all these other legal and moral consequences. Well, let me explain briefly how a typical architecture of a control system is designed. We have this pyramid structure. In the lower level, we have the elements that measure the physical process and that send the orders to this physical process to control. In just the level above, we will have the devices that decide which actions are taken, which orders are sent to these actuators, considering the information provided by the sensors. In the following level, we have the elements that let the staff know what's going on, monitor a part of the system or the whole system to see if everything is going as expected, to be able to see alarms, to see trends, etc. And well, just above that, we will have other levels called management level and business planning that can be understood as something very similar to the things that we see in other information systems. We will have a communication, a horizontal communication between the elements in some cases, especially in the control and supervisory level, but also a vertical communication between the different levels. Well, what's important for us? We will see that we will focus just on this second and third level, the control and supervisory level, because the fifth level will be something somehow unimportant for cybersecurity. We will discuss why. And because in these upper levels, what we have is something very similar to other information systems, and as a result, we just can think of regular cybersecurity instead of industrial cybersecurity. Well, let's see very fast which elements we might find in each of the levels. Well, in the fifth level, we have essentially sensors and actuators. The sensors measure values, physical values from the process, and the actuators act over the physical system. Why is not so important from the point of view of cybersecurity? Well, first of all, we have elements that are very limited computationally, and that sometimes are communicated with the controllers using, for instance, serial communications, and as a result, we sometimes won't have routable protocols that can get into a public network. But that's one of the reasons, but the main reason is that if we need to attack a system, if we are willing to make a physical process work in an unexpected way, it's much more easy to attack or to perform some actions at the control or supervisory levels, where the real actions that the actuators perform are decided. If we are acting at the level of the decision taking, we don't need to act in this way. So let's say that field level is a bit more isolated, but is just a slave to the decisions taken by the control level. And in the control level, what we are using are essentially specific control devices where we have an element that in the shape of these ones that we can see in the picture. There are different types of control systems with different names, as we can see here, but we could say that the most general control device is the programmable logic controller. It's an element with inputs an output that has some programming that is loaded from an engineering workstation, and that is very well designed to well, take decisions from the information it gets from the sensors, but it's not an element with a lot of computational resources or with very let's say sophisticated operating system. Well, in most cases, the problems that we will have is that these PLCs, these programmable logic controllers, won't have almost any security feature. We were talking before about the lifespan of the facilities. Most of the PLCs that are nowadays in the market were designed maybe 20 years ago or 15 years ago, and as a result, they have very limited features. Which are the features that we can usually find in these devices? Well, we can protect the program with a password to avoid the intellectual property theft, but usually this password is not very strong. We will be able to have either a button in the device or the ability to connect an external device through a wire to our system to avoid program overwriting. And in the newest firmware updates of the device, we will probably have disabled some services that might be vulnerable, such as the web or FTP services that were added some years ago to these devices well, they are services that are almost universally unused by the industrial facilities, but they can become a liability because they use very old technologies with a lot of holes. In the best case scenario, and we are talking about the latest, very latest devices that are provided nowadays by the manufacturers, maybe we have the ability to create an access control list, and as a result, limit from which IP addresses the communication can be performed. And in some cases, maybe we have a real firewall or the ability to tunnel or traffic through a virtual private network. But that's not very common. And that's true for any manufacturer. I'm talking about Siemens, I'm talking about Schneider Electric, or well, any other big manufacturer, big player in this market. When we go up in the pyramid, we find the supervisory level, and in this case, we will have essentially two different elements that we can think about. We will have the human-machine interfaces. They are these, let's say, touch panels that are usually available inside of the facility and that are used by the workers in the production line to solve some problems that are appearing during operation, and we will have SCADA systems that are used to monitor the whole control system, and that are able to gather a lot of information from controllers so that we can properly take decisions about our system. Well, in this case, we will have essentially monitoring, but also the ability to act over the system, to send, for instance, manual actions, to change the control strategy that we are using in a certain point. So it will be also very important from a point of view of the targets in a cyber attack. When we are speaking about HMI, we can say that the systems there are very limited, and HMI operators usually don't authenticate. They usually don't authenticate because maybe they need to stop the process fast to avoid an accident, to avoid a damage, and obviously authentication will avoid this fast response. Well, they are usually found in areas with strong physical security, where people will only access through a security control and maybe with an identity card. So, well, they can be vulnerable, but we have this physical security on our side. In the case of SCADA, it is more problematic because it is the, well, let's say the central point or the key point in our architecture, because they will be systems that communicate with all the control devices in our installation, and as a result, if the SCADA system is compromised, we will lose control of our system. We will lose the visibility of our system or even control of it. Well, in the case of SCADAs, we will usually have the SCADA running on a server, on a, let's say, a standard server in a maybe in an IT infrastructure center, and we might have different clients. Some of these clients might be connected from the outside of our network, and as a result, it needs to be protected with care. We need to harden the server to limit the software that is running, block the ports that are unused, and apply any measure that is recommended by either the manufacturer or their standards and so on. And we need to reduce external access to the minimum, and through protected through protected technologies such as virtual private networks. Well, that would be the specific elements that we have in an industrial control system. We were saying that we have some levels above, but in this case, we will have software running on servers or typical workstations that we find in any other corporate network using common communication protocols. In the case of the supervisory level and the control level and the communication between them and to the field level, we will find specific communication protocols. And that's what we are talking now. Well, which kind of communication protocols we will have? We will have what's called field buses, that are the communication protocols between the control devices and the sensors and actuators. And we will have the control level protocols that are used to communicate among control devices or between control devices and SCADAs or HMIs. Well, the names of the name of the field buses has a historical origin that I will not discuss, but essentially, in the beginning, we have serial communication protocols, that is, protocols that are not routable, that cannot pass through an IT network in the way that we know them. But more and more, there are becoming routable protocols that can also have some associated problems. In the case of control level protocols, usually what we have are protocols that are essentially versions or variations of the field buses, because the protocols will be usually grouped in families. And as a result, these control level protocols that are generally routable, that are generally usable through public networks, will inherit the problems that field buses had. Well, we won't speak about the different alternatives that we have. We will just use one of them, which is Modbus as an example. But let's say that we have several technologies competing for the market that are open standards, that are well known, but that are in most cases very old to have security features included. They perform their task very well, but as we said before, we won't have neither encryption nor integrity measures nor authentication. That's the kind of communication protocols that we will use when the control system is operating, when the control system is controlling the industrial process. But we will also have another interaction that we need to have into account. That is that the control devices need to be programmed, need to be configured. And that's done usually through other communication protocols that are specific for each manufacturer, that are not standard protocols, are either proprietary protocols or proprietary extensions of the known standard protocols. But again, they inherit all this lack of security measures, all this, let's say, bad design. And apart from this lack of security measures, in this case, since they are proprietary, from a defensive point of view, it's much more difficult to monitor what's going on and to defend it. And we will sometimes need to use very specific security devices that are able to understand these protocols, because open tools that are used a lot in cybersecurity won't have the ability to understand these protocols, because they are not documented, and anything that we may know about them is information that has been provided directly from the manufacturer or that has been reverse engineered. Well, field buses, as I said before, were originally serial, and they didn't have some of the layers of the protocol stack to route or transport the messages, because we had only one network that was local to us. Well, they were used in the beginning, they are used nowadays in some cases, but they are very fast being substituted by the control level protocols that were used in higher levels of the pyramid. And those control level protocols are routable. They are usually working over Ethernet, the kind of network that we have in our offices or at home. And most of the times they are also going above the TCP IP stack. That is that they are using the same technologies that we find in the internet. Well, these protocols are, as a result, the ones with special interest for cybersecurity. But as we said before, we have these old protocols that are not adapted to nowadays problems, and we don't have any. They are, let's say that they are insecure as design. That will have a big influence on the kind of measures that we take in the case of industrial cybersecurity, because obviously most of these measures will be at the network level and will be focused on isolating these communications as much as possible, because if somebody is able to intercept that communication, not only they will be able to understand the messages, but they will be able to fake those messages and or maybe to make a denial of service. Let's see a specific example, that is Modbus, maybe along with Profibus, Profinet, or DeviceNet and Ethernet IP are the three most common industrial protocols that are found in Europe and America. And well, it is taken as an example for a simple reason that is not only a very common protocol, but it's also the most basic protocol to understand. And we can see how unprotected this protocol is. Well, essentially what we have with Modbus TCP, that will be the routable protocol of this Modbus family, is the frames that were used for the serial communication encapsulated over a TCP IP packet. We have a master-slave communication where the master sends a request and the slave will obey. And that request will usually be either a write request or a read request. In the case of reading, the slave will return the information that the master needs, and in the case of the write, the actuator will execute the command. And well, it's very simple to understand this protocol because we will have just a function code that indicates the kind of action that is taken and a data part that are the parameters in the case of the request and the responses in the case of the response. We don't have any way to verify if the message has been modified in the middle. We don't have any way to hide the contents of our message. We don't have any way to know if the master is really the master, because the slave will obey the command as long as the Modbus packet is correctly constructed. So, since integrity can be checked, we can have replay attacks or man-in-the-middle attacks, which means that in the case of replay attacks, we might see some messages that are not current, but that were recorded and replayed to let monitoring staff think that the process is running perfectly. And in the case of a man-in-the-middle attack, what we have is that somebody acts as the recipient of the message towards the sender and as the sender towards the recipient of the message. So it can change the message and nobody will be able to verify that was the case. And obviously that's the worst case scenario, but even if there's no offensive part of the attack, at least the attacker will be able to understand how our system works, because it's very easy to read, to understand what's going on. In the case of configuration protocols, it's even worse, because sometimes we have this kind of simplistic protocols. For instance, in the case of Schneider Electric, we are using a subset of Modbus to make these configuration messages. But apart from that, or furthermore, we don't have as much information about what's going on because the messages are proprietary. And in this case, in the case of configuration protocols, the kind of things that we can do are even more dangerous. In the case of controlling operation, we are writing values to an actuator. Maybe we are changing the set points that we send to a device. But in the case of a configuration protocol, we might stop the control device completely, or we might change the whole control program or the whole control strategy. So, well, obviously, that's a very important problem in the case of industrial protocols. Apart from these industrial protocols that are used in operation and configuration, there is another technology that is called OPC that is used most of the time to gather information from the SCAD. And this OPC standard, in its early stages, had the same problems that we have with the other industrial protocols. That is that we didn't have any security measure. But there has been a new specification in the last decade called OPC UA that would be, and that's very hard to say, but that is the truth, is the only specific industrial communication technology that nowadays includes some kind of security feature. Well, it was used for this use case that I said before, that the SCADA was gather information from different devices from different manufacturers, and this OPC somehow hid the particularities or the specificities of these control devices. But now, since it is the only good technology, good communication technology from the point of view of cybersecurity that we have, is becoming more and more important, and probably will be widely used in the following years, following this idea of industry 4.0, industrial Internet of Things, or industrial digitalization. Anyway, well, let's keep in mind that we only have one technology that has these security features that we require to be able to provide some kind of security to the communication. Well, since industry is changing very fast, to take advantage of all these IT technologies that were used in other fields, like data analysis, cloud services, augmented reality, and so on, we are seeing some changes in the architecture that we saw before, and in the technologies that we are using. What is the trend? As I said before, we are using more and more OPC UA, but we are also using some other technologies that were not born in the industrial context, and that can be used for other situations, but some technologies that have some security measures and that can be more useful to provide this IT or OT convergence. So, well, things are changing, but as I said before, lifespans are very large in this case, so we will have to deal with the problems that we have for a long time. So let me enter directly in the cybersecurity concepts, leaving apart this idea of how the industrial control systems work and what are the special needs. And well, let's think which are the assets, which are the targets that are important or that can be interesting for an attacker. Well, essentially, from an attacker point of view, the most important targets are the elements found in the control level, the control devices and engineering workstations that we are using to program and configure them, and the elements that we have in the supervisory level. That is the SCADAs and the HMIs and other technologies called historians that are essentially SCADAs that allow us to see into the past of the process. There might be other side targets that would be the network devices and security elements that are used in the network to make everything work. And once we have clear which are the assets that we need to defend, we need to understand the threats that, well, attack these assets by exploiting vulnerabilities. We need to understand which are the vulnerabilities that might affect our assets, and also we need to understand which are the impacts that these assets might suffer under an attack. Because with threats, vulnerabilities, and impacts, we can compute a risk, order the risks that we have, and take some measures to mitigate the most important ones. With respect to the threats, every threat has three parts. We have an agent, the one that executes the threat. We have a vector, how the threat starts, and we have a target. And for a threat to be performed, we need three elements. We need that some skills from the point of view of the attacker, some intention, and an opportunity that is given by the vulnerabilities that we have. We can structure the threats in different categories, but usually we talk about internal or external threats and targeted or untargeted threats. Well, internal threats will be the ones performed by our own staff or third-party staff with access to our network, external from anybody else. Untargeted threats will be the ones that are massive, let's say a malware, a ransomware campaign that is affecting our system because it has some technologies that were the target of that campaign. And targeted threats will be the ones that are designed specifically to damage our system. Which are the typical vectors in the case of industrial cybersecurity? Well, historically, there have been a main vector of attacks that has been social engineering. That means taking advantage of the confidence or of the ignorance of the staff to introduce, for instance, a malware into our system or to compromise an external connection. Usually, social engineering in the most common attacks in the past has been through spear phishing. Spear phishing is sending specially designed emails to staff in our company to make them think that you are their boss or a client and or a provider of services, and to make them start a malware or provide you some confidential information. That has been the case in most of the famous incidents, and in some cases it has been through removable devices, meaning that you have a USB key that you find in the floor or outside of the office, and you decide that it's a very good idea to plug it into the most critical system of your company. Well, that has happened in some cases. And well, obviously, we might have some other vectors, more technical or more, let's say, untechnical, such as just, for instance, stealing somebody's laptop. The initial aims, the initial targets of this initial attack are usually the SCADA servers and historians, because they are usually accessible by some kind of external connection. But it can be Also, the initial aim might be also a network device or the credentials of a VPN that is used for that. Anyway, that would be the initial target and not the end target that will be got by the attackers after some kind of side movement inside the network. Well, which are the specific threats? From the point of view of the control elements, we can alter the firmware of the control device, the programming of the control device, its execution mode, or the communications it has with other elements. In the case of the supervisory elements of the SCADAs, we will usually try to alter the integrity of either the communications or the data that we are storing. From the point of view of specific threats that are very important in the case of industrial cybersecurity, we might think of advanced persistent threats. The kind of threats, the kind of directed attacks made by very capable specialists, sometimes people that are working for intelligence agencies of different countries and that are dedicating a lot of efforts to disrupt the operation of a critical infrastructure. With respect to the vulnerabilities that we might have in an industrial control system, well, we, as in any other information system, might categorize the vulnerabilities in three categories. First, we have the host vulnerabilities, the vulnerabilities that affect the device at a hardware, software, or configuration level. We might have the vulnerabilities that affect the network, the communication between the different hosts. And we might have also vulnerabilities from the way that we formally operate in our company, in our infrastructure. That is, in the policies and procedures that we follow. Every level of the pyramid might face different vulnerabilities, and every kind of specific technology might have different vulnerabilities. But we might see some examples. For instance, in the case of host vulnerabilities, we might have vulnerabilities such as having no physical protection of devices and interfaces, letting an attacker be able to snoop, to get inside of the inner working of the system to understand what's going on. Well, we know what has been done for a long time with, let's say, the PlayStations or whatever to be able to play pirate games. Well, we could do the same with PLCs, for instance. We can have unrestricted removable devices that start, well, infect some malware. We might have our firmware change because we are not monitoring their integrity. We have any kind of problem in the programming of any part that is running in our system might be a vulnerability. We might have software that has no good input validations, that is prone to buffer heap or array overflows, that is vulnerable to SQL injection, etc., and that might be the starting point of an attack. And we will have problems with outdated devices because we might not have patches for our obsolete system, or maybe we didn't install them yet because we were expecting a program stop of our structure, and we might have a bad configuration with unnecessary services that can be used as side channels to our system, for an attacker to our system. We might have also network vulnerabilities. The most important one, as I said before, are the use of insecure protocols. Again, all but OPC UA, but the latest specification of OPC. But we can also have badly designed or documented architecture. We might have our architecture not properly segmented to isolate the critical and the insecure systems from the ones that are more accessible by an attacker. And we can also have a good architecture with good filtering devices that are not properly configured. In the case of policies and procedures, the most important thing is that we might have staff that is not properly trained, that has no good policies to follow, and that might be, as a result, a victim to social engineering attacks. We might have a bad knowledge of our assets, because we will have a great variety of technologies, and it's very difficult to maintain a good management of all of our configuration. And if we don't know exactly what we are running, it's very difficult to know how to defend. And for instance, another example of policies and procedures that might be vulnerable is that we might not be prepared to respond to an incident. We might not have a plan for recovery. The impacts in the case of industrial cybersecurity will be very important, because we have all the impacts that we have in the case of an information system, of a regular information system, but apart, we might have a loss of view, meaning that we don't know what's going on in our system, a loss of communication, meaning that we are not able to solve what's going on there, or a loss of control, meaning that the process that we are trying to control is completely out of control and causing damages to people, equipment, environment, and so on. Well, with all these ideas, threats, assets, vulnerabilities, impacts, we need to do a risk assessment to prioritize risks and mitigate the most important ones, but it's very difficult to do so. It's practically an art, and well, what we need to have, as we will see very fast because we are running out of time, but for us it will be very important to have a methodology to apply some measures. Which are the most common known incidents in this context that we need to know? Well, first of all, we might speak about something that was not an incident, but a proof of concept by the US government. It was done before anyone was worried about this idea of industrial cybersecurity, and they tested if it was possible to cause physical damage just through cyber attacks. It was called Aurora Project. It was done in the Idaho National Laboratory, and well, they were trying to desynchronize a generator with the power network, and well, as you can see, there was some fire in some of the facilities. Well, this was confidential for some time, what made the US government reach the manufacturers and tell them that they didn't needed to take this very seriously. Anyway, for the whole public, it was just a theoretical possibility until the famous Stuxnet incident happened. Stuxnet was a malware that was used apparently to destroy some nuclear enrichment facilities in Iran. That was the first malware oriented specifically to attack control system. It was a very sophisticated malware that was able to infect different operating systems that looked for a certain configuration with specific industrial technologies, and whenever it found this configuration, it made some actions to cause damage. Well, essentially, what it made was changing the velocity of some AC motors that are apparently used in the enrichments of uranium to make them break. Well, it was an example of cybersecurity attack used as a weapon. It was also an example of an advanced persistent threat, because obviously there was someone behind this with enough resources. You can think about Israel, you can think about United States, and well, we could learn some lessons from this attack, but the main one was that it is very difficult to defend against such a sophisticated attack, but in any case, we need to reinforce the network perimeter security, use whitelisting, and monitor security events. Another important event was the first attack to the Ukrainian electricity network. In this case, we had a coordinated attack using malware, but also performing manual actions at a given time. In this case, we had compromised connections from the outside. The attackers had been in the system for enough time to understand how to cause the most important damage, and well, they did every kind of action that can be imagined to render part of the electricity network unusable for some time. There have been other attacks after this one using more sophisticated malware, even having the same well, target as the Ukrainian electricity network. And well, a good example is this crash overriding destroyer that was not focused on a certain manufacturer as it was Stuxnet, but in taking advantage of the specific protocols that are used in any by any manufacturer in this case. Well, we can see that the level of sophistication of these attacks is getting stronger and stronger. So what can we do to mitigate these problems? Well, as I said before, the main thing, the main idea is that we need to have a methodology. We need to have first a way to prioritize the risks, and then a way to know how to select some security measures to mitigate a certain risk. And that's not something trivial, because we have almost infinite possibilities of attacks and almost infinite possibilities of defense. Well, the most common and accepted philosophy in this case is defense in depth, which means that we are taking different measures as different layers of security, thinking that the sum of these different measures provides a multiplicative effect. And which kind of security measures we have? We might secure the data, we might secure the host, that means the device or the computer, we might secure the internal network, the external network, the physical security, obviously, although it's outside of our idea of cybersecurity, and we might also have an improvement of our policies and procedures. There are other philosophies. You have probably heard about resilience, meaning that is not, the focus is not defense. The focus is that our system will resist an attack, provided that it is likely that this attack is finally performed. There are ideas such as zero trust security. That means that we think that everything is compromised and we gain trust dynamically, but obviously these philosophies need to be side to side with the technologies that we have, and sometimes it's not so easy. We also have some standards to follow. The most important one in this case is this IEC 62443, and we have security models devised and presented by the different actors in the field of industrial security. For instance, national security centers or consortiums of manufacturers. Anyway, from the point of view of policies and procedures, what's the most important one? Well, we need to manage the change, to know exactly which are the resources that we have all the time in order to defend them. We need to train and raise awareness with our human resources and with our supply chain, and we need to respond to the incident and recover, and for that we need very clear procedures that our staff will need to follow. With respect to credentials and privileges, we have some ideas that are common to cybersecurity in other fields, but we need to be able to perform them given our technologies that, as we said before, our technology might be old and obsolete. So we need to somehow try to balance what we want with what we have. In the case of security of devices, apart from the physical security of those devices, we need to harden the devices as much as we can. what means hardening? We need to block unnecessary ports and services, apply any security measure that is given to us by the operating system, enable all the authentication and authorization means that we have, and use tools as long as, well, they don't disrupt the availability in our system. Well, we need to have a plan for patches and updates to keep our system as adapted as we can. We need to use only tools that do not disrupt our availability. And with regard to the network security, we need to know very well our perimeter and minimize remote accesses and secure them as much as possible, usually through virtual private networks and using elements such as intrusion prevention systems. We need to segment our internal network, grouping in zones the elements that need to communicate with themselves, and isolating these zones from other zones that are not necessary to avoid somehow this side movement of the attackers. We need to use elements that are able to detect potential intrusions or to block them. In some cases, in the most critical parts of our system, we will just need to rely on detection, because if we block, we lose availability. In other cases, between zones and in the perimeter, we will use some elements that are able to block these communications. And we will use common technologies in other parts of, in other cases of information systems, but also some specific devices, such as the ones that are seen here. This is an StormShield, is an SNI 40, this is a Tofino Xenon, because they will be the ones that will make possible to filter at the application level and not only block IPs and ports, but also messages that are outside of whatever is problematic. And to finish, there's another big and important security measure that is crucial in the case of industrial cybersecurity, that is monitoring of our network. And that we will be able to do that by logging every interesting event and correlating all this information in a way that the security staff can use to either detect current incidents or to analyze past incidents to improve our infrastructure. Well, sorry for being a bit late in finishing this presentation. I don't know if you have any doubt.